Good evening, everyone. Welcome back to all the participants to day 3, session 2. We have with us Dr. Vidyavardhaka, professor from IIT Madras, to enlighten us about R&D in earthquake design and mitigation, along with the professors as panelists. I say no one requires introduction about the gem of structural engineering, most familiar, and an icon, Dr. CVR Murthy, a true benchmark for excellent teaching and research standard of earthquake engineering in India. But still, in short, let us listen about Dr. CVR Murthy, sir, from Ms. Madhushri C., Assistant Professor of Department of Civil Engineering, to welcome the gathering and brief us about Dr. CVR Murthy. Ma'am, over to you.
Thank you, Kanmani Madam. Good evening. Thanks to each and every one of you for being here with us today. I'm very pleased to welcome everyone present on the occasion of the 6th lecture of online training program on futuristic research in disaster resilience being organized by Vidyavardhaka College of Engineering, Mysuru, and National Institute of Disaster Management, Ministry of Home Affairs, Government of India, New Delhi. First of all, I have pleasure in welcoming the eminent researcher, a great teacher and today's speaker, Dr. CVR Murthy, for the occasion. Welcome to you, sir. I also welcome Professor Chandan Ghosh of National Institute of Disaster Management, New Delhi, Dr. S.K. Prasad, HOD, Department of Civil Engineering, DC, Mysuru, Dr. H.S. Dayananda, Dean Academic Affairs, Dr. Umesha P.K., Professor Kanmani S.S. and Professor Rigour S.S., coordinators of Research Studio, Department of Civil Engineering. I take this opportunity to welcome guests, all my colleagues and dear students. Most important of any activity is the participants. I know all of you have come together in large numbers to listen to Dr. CVR Murthy. I wholeheartedly welcome you all. I welcome each and everyone. I have a pleasant duty to perform, that is to introduce Dr. CVR Murthy to all of you. He doesn't need any introduction, and I also have cut short stating many of his achievements. Dr. CVR Murthy is a professor in the Department of Civil Engineering at Indian Institute of Technology, Madras, Chennai. He earned his Bachelor of Technology in Civil Engineering in the year 1984 from Indian Institute of Technology, Madras, Master of Technology in Civil Engineering in the year 1986, also from Indian Institute of Technology, Madras, and Doctor of Philosophy in the year 1992 from California Institute of Technology, Pasadena, California, USA. His area of interest are nonlinear behavior of structures, displacement-based earthquake-resistant design of buildings and bridges, seismic codes. He has over 85 publications in Scopus Status journals and many international journal publications. He is currently the chairman of Earthquake Engineering Sectional Committee CET 39, Bureau of Indian Standards, Government of India 2020. Dr. CVR Murthy has received many awards, some of which are 2018 ICI Best Paper Award, 2016 ACC Nagadi Award, 2016 ICI Best Paper Award, Best Teacher Award, Indian Institute of Technology, Hyderabad in 2009, Distinguished Teacher Award, Indian Institute of Technology, Kanpur in 2008. I deemed it an honor to present you to the audience for delivering the second lecture of third day of online training program on futuristic research in disaster resilience. Over to you, sir.
Good evening, madam. Thank you very much for the warm introduction.
Thank you, Professor Madhushri ma'am. Just a minute, sir. CVR Murthy, sir. I have few things to tell to our participants. Just a few seconds I will take. Okay, dear participants, if you have any queries to ask our speaker, you can post them in our chat box along with your name and location. Those questions will be taken by our panelists after the presentation. And feedback links will be posted in the chat box. Kindly give your valuable feedbacks. So dear participants, kindly note that the e-certificates will be issued to those who have registered in NIDM portal and on the submission of all feedbacks. Now, without further ado, I now request Dr. CVR Murthy, sir, to handle the session. Over to you, sir.
Thank you, madam. Good evening, ladies and gentlemen. Thank you for the opportunity to share with you a little understanding on the research and development in earthquake disaster mitigation. I start with the statement that it's essential for India, and I start with the limited agenda of research and development. As we go along, let's see if this agenda is sufficient or we need to expand this agenda. So today I will talk about, primarily I'll focus on safety. And when I say safety, it is structural safety. That will be the one single focus of the entire presentation. The two steps that I will propose is that we need to learn and we need to implement. And the three needs that I'll clarify will be comprehensive capacity development, use of tested technologies, and implementation of a strong techno-legal regime. I must say that these three are the primary drivers of earthquake disaster mitigation, without which it would be difficult for a nation of this size, which has already got such a large amount of the built environment in place, to become earthquake resistant. So let's begin with the basics. I'll start with the fact that we have a lot of activities before the event, and suddenly there is an event, and then we have a lot of activities after the event. Clearly, before the event, normal expectation is we can prevent the disaster. But earthquake is one disaster where prevention, a word, is rarely used. And if it is used in a very limited context, but not to stop the earthquake, but to reduce the disaster. But the key effort will be mitigation, which is making the built environment capable to resist the strong earthquake shaking that is expected. Preparedness, which is bringing people together and making them ready to face the eventuality of an earthquake, strong earthquake shaking. But the event has happened, and after that we will need to do response. We will have to rehabilitate the people and also do some reconstruction for the lost built environment. In this entire cycle of disaster management, what is in our focus is actually mitigation and preparedness. These two are the ones that will require 80% of our effort. And if we haven't put that in, then it will swap seats with response, and we will have to do 80% will be response. But unfortunately, we would have lost lives and we would have lost a lot of property. But if you want to reduce the post-earthquake effort, these are the two items that we need to focus on, especially on earthquake disaster management. So we are in a threatening situation with the ocean next to us, threatening with floods, and we have a big mountain next to us threatening with a landslide, and we want to come out of this and we want to go far away to the right hand side. How do we go there? We have two options. One is we put a ladder and we do large work suddenly, or we take the difficult path of facing these natural scenarios and the threats and losses to some extent, and then build a very, very robust pathway to safety. And this is the second path that we have. So in the second path, what we are noticing is we have to do small little work all the time and without any rest. This is the entire picture that I want to share with you today, that if you do response, rehabilitation, and reconstruction, you are putting ladders and you're reaching not the destination, but somewhere far away from the destination. So we haven't solved the problem if you do response, rehabilitation, reconstruction. And if you do mitigation and preparedness, then that is the only sustainable path for us to reach a state of being prepared to face earthquakes. So this clarifies the path of the disaster management cycle and the importance of the two elements, mitigation and preparedness. Now, we could have done large amount of mitigation and preparedness and kept the earthquake disaster very local effect. But if we don't do our hard work, we'll spread it as a disaster of the state, of the nation, or even sometimes internationally. What is very clear is that if we don't do any mitigation, then the game is over, and we are actually inviting a level 3 trouble for all of us, where we may even need to get international support. This is not the intent of disaster management in this country. We would like to ensure that this an event in a local scenario does not become an international matter. So earthquake has happened. We haven't done much. What will it affect? It will affect people, it will affect property, and it will affect performance. Now, if you're looking at these three, the three sets of people, the Trident of India, which can help reduce the losses of people, property, and performance, will be the academia, industry, and government together. Very clearly, out of these three items, if you can fix property, you will be able to reduce loss of life of people as well as improve the performance post the earthquake. So earthquake disaster mitigation, what does it have? What does it entail, earthquake disaster mitigation? It can be seen in 5 verticals. We'll call it typology, education, safety, practice, and policy. Typology means you need to know your built environment and you need to have an inventory of all the various constructions that we have. Then we need to have manuals of good practice, technical education. We need to outlaw unsafe typologies. We need to come up with new technologies, do full-scale testing because earthquake is a nonlinear problem. We can't do scale model testing. We need to develop skills in the artisans, do continuing education of professional engineers, undertake retrofit, develop standards. And finally, we need to change bylaws, license engineers, do peer review of all the structural safety designs that are submitted to municipal offices, assess risk regularly, and show that index to the people on the level of preparedness that we are in, and eventually to regulate all of it, a Structural Safety Act. Now let's divide this work into the three, the trident that we have identified, and that will be the division line primary responsibility. Even though every of those three groups will participate in all the elements here, but the primary responsibility lies here. The industry will take the safety and practice part of it, which is to do with the skills and implementation of skills and practice. Government will take the policy part of it, which is to do with the attitude of the people. And then academia will take the education and the typology and the inventory part of it. And that is the game of academia, which is to do with knowledge. So knowledge, skills, and attitude are together going to make this country a competent nation. You can understand here that in mitigation, it's not one of these items. If you do, you haven't done enough. You have to do all of these items, and there is no sequence. You have to start off on all of them, and eventually it will improve. Very clearly, if you look at today's condition, we may have made a beginning in each of them, but we have not made progress in any of them. That is the status that we are in today. Talking about built environment here, there are basic tenets for built environment. It has to be minimal. It can't be too many buildings and structures and not utilized. It has to be minimal. It has to be based on natural materials. It has to be having disaster resistant features, and it must respect nature. So there is an issue of compliance with nature, especially earthquake, which is displacement loading and not force loading. Coming to structural safety, the built environment has fundamental tenets to be followed, which is safety, functionality, durability, aesthetics, and economy. Very clearly, the first three are non-negotiable, and the only option that you have is you can put economy ahead or you can put aesthetics ahead. But number one driving seat is safety, then functionality, then durability. The order cannot be changed and the seriousness cannot be altered. And the number 4 and 5 is the only place where you will be able to do a negotiation. If you pay more money, you will get higher aesthetics. If you pay less money, you will get lesser aesthetics. As straightforward as that, right? But the key is that you need to keep safety on the driving seat, which is different from what we are doing till date. So it's best to go on wisdom, and wisdom tells us many things. First, it says don't make known mistakes. And so what are these items that we have to make sure? We need to make sure that the people, the manpower is competent. 2, the land use is based on past experiences and the projected risk at different places. For example, this case that when the river is going to go into full spate and it's going to flood, why would you build in low-lying areas? We need to pick materials. It's very exciting today to use high-strength materials, but they are the most dangerous materials to use because they are engineered materials. They are brittle. and we don't do any experiments, and we are going ahead and using them without even standards permitting the use of them. So jumping the gun by the industry is not doing good to this nation as we are conducting ourselves today. Second, a large number of untested technologies are borrowed from international environments. They may be applicable to non-seismic countries, but are being grafted into this country. And so this is another area that we have to be extremely careful and wary about, simply borrowing technology from international environment. Compliance. I think we need to have a mechanism for ensuring compliance of the basic safety standards that are laid down in this country, whether they are being adopted or not. So you would say, such a big task, how would you go about? Well, we'll start with an imperfect situation and build towards a perfect situation. So I'll call the start itself as an imperfect start. So how do we go about it? 80% of progress can be made by simply applying available knowledge. 15% progress additional can be made by adapting available knowledge to the Indian environment, and 5% will be generating new knowledge. Let me elaborate on this a little more. This Trident that we're talking about here, 80% is applying available knowledge to the Indian environment, is all about education, right? 15% that we're talking about is adapting available knowledge to the Indian conditions, is about development. And it is this 5%, which is to generate new knowledge for Indian requirements, is the research part. So it's education, research, and development that is going to make it happen. I would guarantee you that if you do only research, India is not going to progress. In earthquake resistant design and earthquake safety, if India has to become safe, only research will not take us anywhere. What we need is a parallel walk on all the three fronts, which is education, research, and development. The simple truth is, no college in this country teaches earthquake resistant design as a mandatory curriculum at the undergraduate program. With that harsh truth, it would be improper to build the 7th story of the building without building the first 6. And hence, we need to have strong foundations for doing strong R&D in this country. Education will involve technical education, preparing teachers and students, continuing education, which is supporting those who have already graduated from the universities and institutes, skill enhancement of the artisans, sensitization of the people, and making aware the decision makers of the importance of earthquake disaster mitigation. In research agenda, just blue ocean strategy, everything is still open for us. Hazard assessment is at large. Full-scale testing has not started. Seismic design is not understood. Seismic retrofitting has not begun. Indian standards are just about getting started, right? And finally, on the adaptation side, on the development side, we need bylaws that are sensitive to earthquake safety. We need licensing of engineers, because virtues cannot be regulated. We need to get good people who are intent to do good work. We need to have peer review in the municipal offices of every design that is submitted, and to make sure that they are doing their work, the peer reviewers, we need to have structural safety audit of 5% or some limited number, so that we know that the process is going on successfully. The checks and balances are essential, and eventually we need to learn to estimate risk and see whether our initiatives are reducing risk over time. I'll take each of these or some of them, select items one by one today, and share with you the scenario right now. If you look at hazard, we will take all the loads into random and non-random loads. And I hope you know the list of random and non-random loads, right? On the left-hand side is the classical loads that we have: dead, live, snow, and so on. And on the right-hand side, we would have wind, blast, and earthquake. The ones in the green are displacement loading or strain loading. And this is not taught in the colleges, how to do structural analysis for this. In the normal context, it's not taught. And hence, especially earthquake safety, earthquake analysis is something that one is learning by oneself without any formal support in this. And if you keep this as an elective for too long, people will have illusion that they know the subject. Now, when you look at this non-random loads, they follow a certain binomial distribution. But when you look at the random loads, they follow a Poisson distribution. So on the left-hand side, we say we want to have 95% of the cases, the load has to be less than this. This is what we say as characteristic load. And on the right-hand side, we need to know what probability of exceedance should we take for that load level to be acceptable for us. But as of today, in the standards, we call them design loads. They are considered values, but not characteristic values, because we have not stated clearly what is our agenda. Are we saying 95% of the cases? Then in that case, are we taking correspondingly the statistical analysis? This is where we will need to do a lot of introspection and relook at the way we are defining our loads. Talking about hazard and probability, especially in the case of earthquakes, if you take a site, that may be the hazard curve, that if you're looking at different levels of probability, and the force, the acceleration that you will design for will be given by this curve. Fair enough. And if you're designing buildings, you will say, no, I will take this level of hazard. And if I'm designing important structures like hospitals, I will take a higher level. And if I'm designing critical structures which are related to utilities or services, transport, water, power, communication, gas, and so on, I will take much higher. And if we are looking at special structures like dams and nuclear power plants, we'll have to say, we don't tell lies, we'll take the whole truth and nothing but the truth. We'll go with the full hazard that is estimated at the site, right? Now, in this scenario, these are the numbers which are conceptually in place. But have we done such a rigorous work? Answer is no, we haven't done this seriously to set exact values of probability for each of these items. That effort is to be done, and we need to do it urgently. Another important aspect which has been missed out in today's earthquake hazard assessment in the country is that if you look at the Indian plate colliding with the Eurasian plate, there are plate boundaries at the Andaman Nicobar. There is some amount of the interplate boundary proximity in the Kutch, Gujarat also. But we are faced with our Himalayan arc, and the Himalayan arc has some special features. What is that special feature? During an earthquake, the plate moves out and comes back. And so there is a movement which is not a straight movement, but it's a going out and coming and opening and closing movement that happens. The impact of this in the fault parallel direction is shown to you as a pulse effect in the accelerogram. And in the perpendicular direction is again another pulse effect. If you see the velocity diagram, you will notice that velocities up to 2 meters per second are already recorded in the past earthquakes. Accelerations up to 3.2 G are already recorded in the past earthquakes. Slips up to 700, 800 mm, 1 meter are already recorded in the past earthquakes at the location where we are looking at the slips are happening of the instrument, where the instrument is located. If you go almost onto the site, onto the fault rupture zone, the numbers can go much higher, up to 3 meters, 5 meters, or 10 meters. Talking about seismic hazard assessment, we are still at the beginning. We have high magnitude earthquakes, but we don't have any records in this country. We have low magnitude earthquakes, but we have very limited records, and they are not adequately shared with everybody. So a large amount of work has to happen on the physics of the earthquakes and the design earthquake hazard, especially not just acceleration hazard, but also displacement hazard. We have to come up with that. So this is the difference. On normal classical earthquake hazard is on the left-hand side, which is acceleration based. But in time ahead, we have to do displacement hazard because the whole country is now crossed by large number of pipelines and electrical transmission wires and tunnels and so on, that now we need to know how much is the displacement so that these linear structures can be designed to resist the slip that is likely to occur across those faults. Also, we notice that at the collision of the Indian plate with the Eurasian plate, there is a large sediment of ocean bottom sandy material, and that is the one that is going to cause additional challenges of geotechnical engineering. So geotechnical engineering has to do another takeoff in this country. We need to do a lot more hard work, organized hard work, and that is because if you see, as Indian plate comes and collides with the Himalayas, the lesser, middle, and the higher Himalayas are formed. And you notice that as you go from Jabalpur to Kanpur to Lucknow to Gorakhpur and up to the hills, the depth of the sediment will vary from 0 to about 7-8 kilometers or even higher. In that scenario, the sediment depth is such that the natural period of the site will go from half a second to about 7 seconds in the Himalayan wedge. If that is the story, you're looking at different structures which have different natural periods, will be picked up by the earthquake shaking, and we will get serious damage inflicted on them. So clearly, we need regulations that are sensitive to the site effects that are likely in the different locations at river mouths in India, or lake beds that we are building on, and so on, that we need to be very careful about land use development in time ahead. The word multi-hazard has come on suddenly, and it looks like as if it's a new monster. Answer is no, it's not a new monster. We've always been doing multi-hazard, just that it is fashionable to say it so today. And we have been handling in the yesteryears, we've handled wind, we have handled waves, we have handled earthquakes all together. But somehow we never made noise about it. But today we are making a lot of noise about it. Why? Because in education, we are not teaching them the integration of the design process in which all the hazards have to be considered. Every class teaches only one hazard, and there is an impression in the students that we need to do one hazard at a time. Earthquake resistant design has grown over time, and it has always been a multi-hazard resistant design. One of the important things is that there are two segments to earthquake resistant design. One is defiant design, and the second one is compliant design. I showed you the forces, the loads that are appearing. One is called the force load, and the earthquake is the displacement load. So we have to be very careful when we do displacement loads. We'll need to watch out whether we need to do compliant design or this defiant design. In fact, the truth is, might is not always right. And if you go back into books of history, they made massive structures, and come earthquake, the entire built environment, which is made of masonry, brick over brick, stone over stone, has come down. In fact, dynasties have collapsed. In fact, 8.5 lakh people died in just one event in the past, in 1500s. That is the kind of severity that we are expecting if we continue to build with the brute force method of might is right. But the bottom line is, it's not might, but it's nature that's always right. And we need to respect nature and understand nature, mimic nature to the extent we can. So how do we do that? In earthquake resistant design, we need a closed loop design method. So we know our materials, we design sections, and we design members. This is B.Tech and M.Tech. And then you go to construction, you do detailing, and then you construct the structure. But what is actually required is that you need to know what structure you have designed, how it will behave, and what will be the damage that will be inflicted in it. So currently, in today's education process, we are only doing the forward loop, and we have not done the backward loop. We are not doing the backward loop. Unless we do the backward loop, we don't know the design that we have given to the people is safe or not. And this is where we need to give a holistic view to our students and teachers. They need to understand that earthquake is not a force, it's a displacement, and we need to ensure that there's enough deformation capacity in the structure to resist the displacement that is imposed, and that earthquake doesn't apply forces. Forces are induced because of inertia. All this has to happen calmly, and it will take time. And there has to be priority to teach earthquake safety to the people of India. There are 7 virtues of earthquake resistant structures. And if you believe this, the first virtue is that it has to be a simple configuration. Structure has to be simple in geometry and structural system and the use of non-structural elements. The second one is it must have an assured at least a minimum stiffness, initial stiffness. It must have at least a minimum amount of lateral strength. It must have at least a reasonable ductility and a guaranteed deformability in the structure. And it should lead to a desirable collapse mechanism. But more importantly, we need to ensure that the energy that the earthquake is feeding is absorbed by the structure. And these are the 7 virtues that the structure has to now be capable of in the path of trying to resist earthquakes without collapse. So what are the design methods? The 4 levels of design methods. We started with stiffness-based design. We are currently in the strength-based design. We are poised to get deformation-based design in place, and we are a little away from the energy-based design method, right? That is discontinued already. The stiffness-based design is discontinued. Currently in practice is strength-based design. Currently under development, where the focus is on collapse mechanisms and deformability. This is what is the hottest topic right now for research. And in time ahead, we will not only worry about collapse mechanisms, deformability, but we'll also talk about energy absorption in structures. So we are at level 2 right now. We need to go to level 3 and level 4. And hopefully this will mean a lot of hard work for all of us, which we will do happily. Let's understand vulnerability a little bit. Vulnerability is the incapability of the built environment to resist earthquake shaking. Let's take 3 examples: wind, flood, and earthquake. And let's take 3 structures. In wind and in a wave and in earthquake, what happens? In the first, the wind is going to suck the structural components away up into the sky. In flood, it is going to topple the structure, and in earthquake, it's going to bring it down vertically, right? For very clearly, we need the structure to be having such mass that the large uplift forces are contained. Again, on the flood case, the overturning has to be reduced, so we need to have wide base and reasonable mass also. And in earthquake, it has to be light, and it cannot draw so much of inertia forces. So we need large mass for wind, we need large mass for flood, but we need small mass for earthquake. Now, how does a designer do all of this? That in the same location where there is wind and earthquake, how does a designer say what is large mass for wind, large enough for wind, but small enough for earthquake? This is the magic that R&D has to say. What is the optimal mass? What is the optimal design? What is the best design that can resist both of them? Indian standards, the picture is very clear. We have about 2,000 standards, just say, let's say buildings alone, and 400 are related to safety, and only about 10 of them are related to earthquake safety, right? In this 200, almost all the items come into picture. But in the safety list, there the 3 focus elements are estimating hazard and analysis, design and detailing, and assessment and retrofitting. This is where the 3 standards are focusing right now. But then even there, it's largely related to buildings, and the other non-building structures, we need to develop those components. A new habit has to begin, that the standards are prepared, draft standards are prepared by practicing professionals and proactively brought to the Bureau of Indian Standards, so that these clauses can be included based on the considerations that they are experiencing and during practice. Of course, we need to increase the number of academics and professionals who are engaged in the development of standards. So what is the status today on, let's say, the same 3 elements of nature? Wind is seasonal, flood is annual, earthquake is rare. So how are we behaving? We are addressing wind to some extent, but flood we are disrespecting. We are constructing in low-lying areas. And earthquake, we are not fearing, and we go on despite the past experiences. 2001, we lost 13,805 people, and we lost a huge amount of infrastructure and heritage property. But have we really taken action forward from 2001 onwards? Right? So what are the gap areas? When you look at earthquake safety, in wind, the behavior is supposed to be elastic. Fair enough. But in earthquake, the behavior is supposed to be inelastic. So the force loading of wind, there is an upper limit, and it can be determined deterministically, and there is sufficient data for that. You can go with a value and be happy about it, that you are not going to make a mistake on that. But when it comes to earthquake, the loading is displacement, and this upper limit is not determinable and deterministically. We have to go probabilistically. And also we have insufficient data even to do probabilistic estimate. So we are in trouble. We have shortage of knowledge here. As you can see, nonlinear behavior of the structure during earthquakes. This is not taught. Nonlinear analysis is not taught in colleges as mandatory curriculum. So how do you expect engineers to be knowing nonlinear analysis? So they will take the computer software, press any button, and be happy about it and make others happy about it. Very good. But what is the truth? Only time will tell. Exposure. If you want to see the risk assessment, there is a strong need to understand how much of exposure are we providing to the earthquake of the people, property, downtime, and business continuity. For example, in this picture, in the middle of the desert, if you have an earthquake, no sweat, there is no exposure, zero. But if you add buildings and structures here, then what happens? Then you're putting people, property, you're worried about downtime, and you're worried about business continuity. And according to this, there'll be human risk, property risk, financial risk, and business risk. And the way to control all of this is bylaws. So bylaws should be written a lot more carefully with a holistic picture in mind as to how much risk are we putting our people into, right? Because exposure is one of the important components of risk. And if you indiscriminately keep increasing FSI in buildings and structures, you can actually harm the people's life by unduly putting large amount of people in structures that are actually vulnerable to earthquake shaking. So talking about risk, the three components of risk: hazard, vulnerability, and exposure. Hazard is controlled by science, vulnerability is controlled by structural engineering and geotechnical engineering, and exposure is controlled by bylaws. Right? This together is our game of earthquake risk, and we need to be very, very careful. So today's situation is that under the probable likely events, the shaking, the impact has been such that we are seeing extreme risk under intensity 7 shaking. 220 kilometers away in Ahmedabad, when the 2001 earthquake came, intensity of shaking was 7, but we had 132 multi-story buildings collapse. Right? That's not the scenario we want. We want the scenario on the right-hand side, that under the probable extreme shaking, we should see only a limited amount of threat in terms of impact. And in most cases, we should get away without much. So the green patches have to be increased, so the impact has to be lesser, and the red patches have to be reduced in time ahead. This can happen only through the earthquake disaster mitigation and no other pathway. Right? We have different structures, and the rigor required for different structures is different. And we need to be very careful as to whether we are applying the higher rigor or we're still striking 2 stones to get fire, even for the case of the important and critical structures. I'll take one example. Technology is a word which is generally the way we practice the use of knowledge in the development of the built environment, right? I'll give you an example of dams. And dams, we need to do field tests, we need to do analytical studies and laboratory tests. But as of now, we're only doing analytical study. We're not doing field tests and laboratory tests related to behavior of dams during strong shaking. Now, if I take just the analytical part alone, we are doing equivalent static method, but there is response spectrum method, pseudo-dynamic method, and dynamic method. We're not doing the right-hand side 3 items. We're only doing the equivalent static method, which is a 1960s item, right? There are 3,500 major dams in the country, and if you're still striking 2 stones to assess their safety, I think we are not doing justice to the people of India. We need to buck up and make sure we implement the correct level of technology when each of these tasks are given. And this is one example I'm giving you of dams, but there are many other examples that we can dwell on and understand the current status. Come retrofit, we need to have very committed individuals who can actually say, I want to do retrofit, and they keep pushing different groups and different organizations, including governmental structures, where retrofit has to be done. Very nice. But more importantly, we need to make sure that the safe structures on the new structures are going to, while they are going to increase, we have to make sure that the existing structures, the unsafety in them has to be reduced, and this can happen only through retrofitting. And retrofitting is a slow process, a tedious process. It's not going to be as fast as to make newer structures safe, but it requires a higher level of engineering, and we need technologies for retrofitting. And as of now, there are a lot of people who are saying that if you can do component level retrofit, you will be able to save the structure by either jacketing or wrapping and so on. But the key issue is the holistic parameters like the lateral stiffness of the whole structure, lateral strength of the whole structure, lateral deformability of the whole structure. These are the questions that we have to answer, and simply wrapping away one column will not alter any of the global parameters of the structure. So there's a large inventory of critical structures, lifeline structures, schools and houses that we need to retrofit, and we don't have hands for that across the country. So we need a lot more energy to come up on that. And to assess the existing structures, we need methods, and we have 4 levels of methods: rapid qualitative, detailed qualitative, simple quantitative, and detailed quantitative. There is an illusion that the first level is actually to assess safety. No, it's not. It's only to screen. The safety is assessed only by the quantitative methods, which is level 3 and level 4 methods. Level 1 and 2 only give you screening procedures. They are not going to tell you whether the structure is safe or not. It says that prima facie, it doesn't have the required features. That's all. But the level of unsafety can be assured only through quantitative measures. And I would urge that we should start at level 3 urgently to get started on the people to understand what is retrofitting. What is important to understand is that when you talk about retrofit, level 1, the rigor required is lesser, level 2 is little more, level 3 is furthermore, level 4 is even higher. But more importantly, the time taken for level 1, 2 and 3 are very different, and 4. In 4, you require large amount of time. So obviously, when you do level 1, 2, 3, 4, there has to be a strategy. And the strategy is, if you take 1,000 buildings in level 1, 100 of them will be taken to level 2, saying that they need to be retrofitted. Out of that, 10 will be taken to level 3, saying they need to be retrofitted. And out of that, 1 will be taken for retrofit at the level 4, which means if you're looking at a 330 crore houses that we have in the country, 80% are sitting in seismic areas, which is like 25 crores. So 25 crores, 25 crores, if you start doing work on them, even if you take 1% of that, that means 25 lakhs, 25 lakh houses. Obviously, 25 lakh will become 2.5 lakh, will become 25,000, will become 2,500. To fix 2,500 structures, do we have enough people in India? That is the question that we need to answer urgently, so that the work of earthquake retrofitting can begin. Techniques, you would understand that there is retrofitting, there is rehabilitation and repair, right? And in retrofitting, there is structure capacity getting altered. In rehabilitation, functional use is getting altered. And in repair, visual improvement is getting altered. Structure capacity can be to restore it back to original condition, upgrade it to a higher level, or even remodel the structure. But very clearly, one lesson learned is repair is not retrofit. So anybody who is selling repair in the name of retrofit, you better be careful. This is another market which has grown aggressively, and for want of people who understand the subject, they are getting away with anything that they are selling. The process of retrofit is simple. There are set procedures for that, and it's hard work. Process is simple, hard work it is. That's all. So the bottom line is new structures. If you want to reduce the earthquake disasters, new structures should have peer review of their designs, and technologies should be proposed with R&D backing, and type design should be done only if fully they're tested to full-scale structures. In fact, we have only 2 facilities in the country today that can do full-scale testing of 3-story houses or even a 15-meter long bridge. We don't have more than that. So for 132 crores people, 2 facilities is too small. Another issue for us is existing structures. We need to assess them. We need to have nonlinear analysis skills. We need to learn strengthening and the retrofit measures that have to be undertaken. And we have to start with pilot projects. We can't go whole hog. You have to nibble the mountain, not gobble the mountain. And bottom line, to do all of this, is competent engineers. We need to make sound appointments, and we need to train the graduate engineers, continue to do continuing education, but bottom line is licensing of engineers. If the engineers don't pass an exam every regularly, 2 years, 3 years, 5 years, whatever, then you're saying that we don't have safe hands. Competence is something that you can develop in 5 cycles over a lifetime, in childhood, in school, college, employment, and in retirement. It's a lifetime activity, and we need to be sensitive to the improvement at each level and who is responsible for the competence development at each level. As you can understand, from childhood to retirement, the responsibility goes from others to yourself as you go from left to right here. Talking about competence, out of the entire civil engineering workforce that we have, or engineering workforce that we have, about 84% are workers and supervisors, and about 4% are engineers and 2% are managers, right? What we need to do is skill development for the 84%, and we need to do continuing education for the 6% that we have. This is the hard work that we have to do. But where are the teachers who can do this work? Capacity development. Making mistakes is something that we have been noticing, but these mistakes arise from incompetence, ignorance, and willful inaction. This is a reactive issue, and this is not the development agenda. The development agenda is a proactive one where known mistakes are not made, and the way to control this is quality control and quality assurance. That is how we will do capacity development. And just to understand a little more, we are going on, life is going on quietly, and there's an event, we are incapacitated, and then we start hustling and do some post-earthquake response activity because we have done some preparedness. Very good. But if you don't do preparedness, then even that won't happen. But what is important is if you do mitigation and preparedness, that is where you will see, first of all, the setback will be smaller, and second, that we can even spring back to a baseline higher than the baseline that we started with. And that is what is normally understood as build back better. But the key point here is mitigation. You can't get away, you can't do anything positive without mitigation. What's important to recognize is that the recovery time is there only if you have done mitigation. If you do preparedness, there is no recovery time. Infinity is the recovery time. Right? Also, you notice that the dip in your incapacitation will depend on how much mitigation you do. The more mitigation you do, less will be this dip. And we hope that in eventual condition, only the unknown will actually cause this dip, but not the known agendas. So licensing of engineers, if India has to become robust and capable of doing earthquake resilient constructions, then we need to have teachers and structural designers who understand the subject completely. And we need not just degree holders. Degree holders will write examinations and get a license if they pass. And after every 3 years or so, we need to have that agenda. Otherwise, we will not be able to guarantee safety. Structural safety audit, we start now, 2021, in 10 years, we start with a random audit. And eventually by 2031, when we learned the process of audit, as well as we have enough people who can do audit, we can get to a situation where we'll do 100% audit. But right now, we have to start with an imperfect 5% random audit. Third-party peer review is so important. There's a building owner, he wants to build a structure. He has 4 persons who are helping him. And for each of these, the entire set on the left-hand side is actually called quality control. These are the persons who have gone to good colleges, got good education, and they know what to do correctly, and that is quality control. Because they've gone through the system, at least theoretically, and with time they will practice under the tutelage of a senior engineer or senior architect and so on. But what is important is, notwithstanding that they are doing a good job, there is a need to have a planning peer reviewer, design peer reviewer, construction peer reviewer, maintenance peer reviewer, because other people's life is at stake. And so we need to have another group, an independent group called quality assurance group. And this quality assurance group will report directly to the building owner, and that is where the game begins. So it's an independent group, and they will be feeding back to the owner what the truth is. So the owner becomes the first party, quality control becomes the second party, and quality assurance is the third party. And that's why we need third party peer review of all the structural designs when it comes to earthquake safety. So we make a lot of mistakes in life. Yes, let's understand our mistakes. I want to do something. Do I know what has to be done? Answer is yes. Then am I trying to follow that? Answer is no. That's the error of intention I'm getting into. I know what has to be done, but I'm not doing. If I know what I'm trying to do, then am I succeeding? If the answer is no, then that is error of execution. If I am succeeding, then it's successful completion of the task. Very nice. Let's go to the other side. Do I know what has to be done? No. Do I recognize that I don't know? I don't recognize, then that's error of concept, right? If I recognize that I don't know, am I trying to do something about it? If I'm not, then that's error of intention. And if I am doing something about it, am I succeeding? Yes. Then if it is no, then I have to go back and recognize that I don't know what I'm doing. And if I'm succeeding, I will go to the other side, the positive side, closer to your left side, which is your heart side, that you know what has to be done now, and so are you trying to do that? In all this, there are three types of errors that we noticed: error of concept, error of execution, error of intention. So error of intention is the most dangerous of all of them. In fact, you will not come out of it in a court of law if you are shown to have error of intention. This can be corrected through only techno-legal regime. Error of execution can be corrected through licensing of engineers, and error of concept can be corrected through capacity development. And that is where we stand today, that if India has to become robust, we need these three ingredients of earthquake disaster mitigation, these three bottom lines of earthquake disaster mitigation. Complacence is coming into us in many cases, that we know everything, we are doing everything right, and that is because we are hurting in attitude. We don't have positive attitude, we have negative attitude, and that is where we are actually getting into trouble. And if we can correct our attitude to become positive attitude, only then we will be a competent nation. You can have any amount of skill and knowledge, but if your attitude is negative, then you are not competent. You are incompetent, even though you have skills and knowledge. The nation is not getting the best out of you. It's not benefiting from your knowledge or skill because your attitude is not proactive and positive for the good of others. So very clearly, we need to ask for competence: attitude, positive, skill, knowledge, and then only you'll be able to get to competence. Now, all of this will begin with the teachers. And the teachers are at 5 levels. I talked about competence being in 5 cycles from childhood to retirement. And the first set of teachers are parents. Second set is school. Third is college. Fourth is employment. And fifth is yourself, right? I'll stop here and say that we need to make an imperfect start. Very clearly, what we have learned is that the best has become the enemy of good. We are looking for the ideal and not getting started with at least the known agenda. And this is where we urge once again the people of India that, look, we need to do this earthquake disaster mitigation if we have to save people in the next earthquake that's going to come anytime now. If that's the story, then 80% of our progress can be made by simply doing what is good instead of looking for the best, right? So we have to start with the available resources, the good ones amongst them, and go forward with them. And as they would say in Hindi, in Urdu, that kafile jurte gaye, karwan badhta gaya. So men and material, we have to move them with whatever we have and do the best out of that. I start with the agenda saying earthquake disaster mitigation is necessary for India, and I'll use the word must for India now. I will expand the fact that it is not just research and development, that it is education, research and development that is requiring the attention. Knowledge sharing is crucial. Multidisciplinary approach to the problem solving is essential. We need to work with municipalities and making sure that their bylaws are sorted out. their peer reviews are done, and licensing is done through the government. But to help licensing, academia has to come in. And so the trident of academia, industry, and government has to start working and build partnerships across the nation, all the agencies that are there in the game of earthquake disaster mitigation, and when required, internationally also. I will put a statutory warning here that this story will be told till it is learnt by heart, mind, and soul, because as per the Disaster Management Act, we are mandated to do the earthquake disaster mitigation. So if we, till the day we learn it, we will keep repeating this story in different forms, in different language, in different tenors, in different orientation. Very clearly, nature is going to throw 5 salvos at us, right? And nature is also watching us. But what is interesting is that we have become paper tigers. And by doing paperwork, we don't make structure safe, right? We need to make sure that we get the big picture right of the demand as well as of the capacity. Only when you get the demand and demand on the structure and capacity of the structure in place, then you will be able to do meaningful contribution to earthquake disaster mitigation. In the next 30 years, India is going to grow. If we don't change our strategies, we will be 180 crores people from 132 today. But if we are very active, we can become 200. If you're super active, we can become 250 crores. These are the projected limits of the potential population that can grow. So in that case, we need to be very careful that the built environment required for so many people has to be created. At least the additional built environment that we will create has to be made disaster resilient, earthquake resilient. And that is where the challenge is, that explosion of infrastructure development and housing is happening. But if we don't correct the method now, we will have more unsafe structures in front of us. So it's not time to be a spectator, it's time to get onto the play field. I would pray that the ones who are playing should go sit in the galleries and the rest all should come down below, because we need large number of hands. Conditions are tough, it's not easy, but hard work can take us forward. There's only one choice that we have to make, which is called the considered choice, which is mitigation. The more you do mitigation, the less response you'll do, and vice versa. So it is wise to invest before than to pay later. In 2005, the Act came. In 9, the policy came. In 19, the plan came. And from 2007, we have been having the earthquake disaster management guidelines, but we haven't gotten started yet. So we need a earthquake disaster mitigation education, research and development program, and a comprehensive one, wherein all the Trident will come together to make it happen. The industries, the governments of India, states and UTs, academic institutes, universities, and R&D organizations. And if you ask me when, it's due. And it's due long time back. At least get started now. As we finish this lecture today, let's get started. But the key point is, don't expect that you'll wait for somebody else to tell you what to do. You start walking and others will follow you. Akla chalo re. That is what is the game by Rabindranath Tagore, what he taught us, that even if there is nobody around you, you should start walking, right? Because our dream is to build a disaster resilient India, an earthquake resilient India. And so we need to do this for our own safety, for the safety of our children and the safety of the generations to come. Ladies and gentlemen, I must say that this can happen only if we go from untruth to truth, from darkness to light, and from life to eternity. And this is there in our classical training. And so I pray that we will follow that verbatim in letter, spirit, and action. I'll stop here by thanking Professor Prasad for the affectionate invitation, and also the College of Vidyavardhaka, College of Engineering, Mysuru, and the colleagues to have given me this platform to share the thought today with each one of you. Ladies and gentlemen, thank you for your time and attention. Jai Hind.
Thank you.
Thank you, sir. Thank you, sir.
Excellent. Okay.
Thank you, sir. So that was indeed an informative, interesting, and motivational session, I should say. We learned a lot in understanding Trident for making competent India and the closed loop design for structural safety, importance of wind, flood, earthquake, and many more concepts to understand impact and consequences of ignoring earthquake disaster mitigation. I say that you really deserve to be the benchmark of teaching, sir. An excellent teacher. Born Teachers Day. Thank you, sir. Thank you so much.
Thank you.
And
Thank you for
and for the participants, just a gentle reminder to you people. You can post your questions in the chat box and give your valuable feedback provided in the chat box. Now, today in this session, we have in our panelists Dr. Chandan Ghosh sir from NIDM, Dr. S.K. Prasad sir, and Dr. Umesha sir from VVCE. I request the professors to handle the question and answer session, sir. Over to you, professors.
Professor C.R. Murthy, you were simply fabulous. Just salutes to you. The way, as he rightly said, born on Teachers Day, really, you're a great teacher. And as you said, maybe we have some 25 crore houses. And then even if you think of 2,500 for capacity evaluation, it takes long time. Likewise, you always told about education, educating people. And we may require at least, 1 lakh Professor C.V.R. Murthis to educate, the country on this. So really good. Thank you. Your popularity, your teaching, mesmerizing teaching, is proportional to the number of questions we have now. So I request you to take those questions. Before that, I request my good friend Professor Chandan Ghosh to make his remarks.
The only remark is that Professor Murthy, with his slides, which speak more than he speaks, but what he speaks is more than what his slides indicates, with colorful presentation. And that way, in fact, the way that he has defined, this is after 15 years in NIDM, and we know disaster management, we are doing rather business of disaster management, whereas in NIDM, business of teaching or capacity building. But today's lecture, after so many times, every time I listen to him, today he has given a really definition, not in digital form, but in a colorful way, that what hazard, risk, vulnerability are, and then what is the future, as well as which we have to start from the present right now. As you rightly said, that after this lecture over, let us start. Otherwise, we'll go to 280 crore or something, whatever population, that will not be handled. So in this case, I just want to say that it is really superb, and I think whoever is writing question, probably they should go for another 1 hour of pranayam to go through to consume those things, whatever is being displayed in perfectly 1 hour, in a very professional way, as not only as a teacher, but also as a he is now looking after CED 39, and a lot of things and changes are happening in the professional level also. So we would like to see that as long as he remains active, let COVID doesn't come in between us or in between the society anymore for the third time, anywhere. Of course, so that way we would like to see that let this education and this session that we had, let it vibrate or reverberate within us, within all, whoever looks into. Thank you very much. Really.
Thank you, Dada. Thank you, Dada.
Okay.
Ekla chalo re, huh? Yeah.
Ekla chalo re.
Okay. And Professor Umesha, would you like to add something?
Yeah, I think as usual, Dr. CVR Murthy has given excellent lecture. I think it is a very good, and he has expressed what are the R&D required for the future, and multi-hazard resistance design is required, and also it is required multidisciplinary. All the people from the disciplinary has to come forward to do the research for the earthquake design and all. I think he has given clear idea what has to be there next 30 years for India. I think I will congratulate him and thank him. Thank you, Sir Murthy. I
Thank
think
you,
I will
Professor
back.
Misha. Thank you,
Okay,
Professor
sir.
Misha.
Sir, I think we have about 20 plus minutes. Is it okay to take a few questions? There are
Yeah.
plenty
I'm
of
happy.
questions.
I'm happy to
Okay,
take
okay.
questions.
Yeah. Anyway, before that, there have been many appreciations for you. I just spell out a few of them. From Reza Rafat, enjoyed the presentation, learned too much. It was wonderful, really informative, and highly insightful. God bless you, sir. And from Professor Aravinda Galagali, sir, excellent session and refreshing again after a long gap from my days at IIT Kanpur. So plenty of them are there. Let me just request you to answer a few questions. I start from back. Professor Balaji, Dr. Balaji says performance-based designs or not have not been extensively practiced in India due to enough codal provision guidelines, rather due to lack of codal provision guidelines. Is it to make this performance-based design mandate? If if so, what is the benchmark?
Thank you for the question. Performance-based design requires two things. First of all, you should have designed by the normal procedure properly. And secondly, you should have the tools to do performance-based design, which is nonlinear analysis, nonlinear behavior, full-scale testing, which all of which are missing. So at this point of time, we will continue to hustle to talk about performance-based design, but we will not start performance-based design because there's no critical mass of people. Even if you put a standard in front of you, if there's nobody who can do nonlinear analysis, then there is no way we can go ahead with this performance-based design. Key thing is to remember, performance-based design is the reverse part of the loop, not for forward part of the loop. There are a lot of illusions that performance-based design can be used to reduce the cost. No, that's not the issue. Performance-based design has to be used to improve the performance. That means that we have to guarantee no collapse. Earthquake resistant design philosophy says no collapse, and performance-based design procedures will help you see if indeed there is no collapse or there is going to be a collapse. So what I'm seeking is that let us till the land, sow the seeds, and when the harvest comes, then let us call it performance-based design. Until such time, we have to do a lot of hard work. We have to prepare the teachers, and we have to prepare the graduate engineers, and who will go and then start doing basic retrofit work. And then at the end, we will talk about performance-based design. The sequence is rather hardwired.
Okay. Yeah. Again, a compliment. Professor Vijayendra says that, the record of this should be shared across all civil engineering schools for the benefit of students and teaching faculty. I definitely put in my effort to see that, it is spread across. Definitely, I'll try to do that. From Shibani Jha, wonderful session. Mind is the most beautiful. All right, again in appreciation. I go to the other one. Subramanya R. Sharma and a few others also have asked. IS 1893 Part 1 2016. Okay, the design spectrum is presented only for 5% damping. What about the rest?
Yeah, see, there are two parts here. One is that when you're talking about design procedure, you're looking at buildings, let us say, the damping value is not known to anybody. The initial damping or the structural damping that we call varies in concrete structures from 1 to 2%, And during earthquake, the damping, because of hysteretic energy loss, will climb from 1 to 2% to 5% to 10%, 15, 20, 25%. So which value will you take? So when this confusion arose many decades ago, internationally it has been agreed that let us take 5% and design the structures that are supposed to see damage with 5% damping as the basis for the purpose of design. Now, when it comes to assessment, you will do nonlinear analysis and the hysteretic damping will get added. So you start with the structural damping of 1 to 2% or 3% in that structure, and then let the hysteretic damping come into picture, and whatever is the damage, that level of damping will come in, right? So for design purposes, the value is fixed, but for others, the value is, for assessment, the value is going to come through the process. Now, having said that, you might argue that different structures have different initial damping. That is true. But if you're allowing ductility to be the basis and large damage is being allowed in that, then you will see that you can't get biased for steel structures, concrete structures, and masonry structures. If you give different damping values, you are biasing the country to build only concrete structures. That's what we did earlier. When we penalize steel structures by 40% extra force by saying steel structures will be designed for 2% and concrete structures will be designed for 5%, we penalized. So steel never got started off. Now by removing that penalty, now there will be competition between steel and concrete structures. Sir.
Thank you, sir. Professor Mangala Keshav says, should we emulate from successful stories from other countries? If so, can you state some examples?
Yeah, I went to some country and they said, don't put your fingers in that electrical socket because it gives shock. And I learned it. And I will follow that for life. Right? So where is the wisdom says that you have to learn from other people's experience. There is no choice here. Should we emulate? There's no question here. And I must say this, that every country has gone through very difficult time. And they have taught us how to do different things, right? For example, in 1972, there was an earthquake in US where until such time, they were thinking that bridges and buildings are designed by the same philosophy, that horizontal members will get damaged. In 72, it showed that the vertical members will get damaged in bridges, and horizontal members alone should be damaged in buildings and not vertical members. So the principles of philosophy of design also were learned through experiences in the past earthquakes.
Okay. Yeah, I welcome Professor Mahendra Singh.
Namaskar.
Very nice, sir. Very nice. Excellent. In fact, Professor CVR Murthy, Dr. Umesh are from IIT Madras, and myself, Chandan Ghosh and Mahendra Singh, we used to be at IIT Kanpur. Almost contemporaries.
Okay.
Excellent. Okay.
So I can see a nexus here. I'm also from Kanpur.
Yeah. You belong to both. Exactly, sir. And then, I'll just go to the next question from Sangeeta Pandey. Are load-bearing structures no more recommended nowadays?
I would say this. Load-bearing structures will remain for life. The only question is, unreinforced load-bearing structures should not be built anymore. But reinforced load-bearing structures should be built, which means that masonry, brick over brick, stone over stone, will kill people. So we should avoid those, but we should reinforce them. There are techniques for that. For example, confined masonry is one such technique. Strapping is another technique, and so on. That we need to adopt those to make sure that the people who are not able to make expensive structures and whatever they are able to build, they are all safe. And this is our responsibility.
Okay. Yeah, a question from Meghashri. Is it required to perform seismic analysis of ancient masonry or concrete bridges about 70 to 100-year-old in zone 2?
Yeah, see, the catch is today's zonation is based on past earthquakes. If you look at 1993 Killari earthquake or the Koina earthquake, they were all surprise earthquakes. And if a surprise earthquake happens, you don't want to lose a bridge. So my personal appeal will be that we need to assess all critical and lifeline structures, even if they are so-called in the current seismic zone 2, we need to assess them. And this is also an occasion to learn the process. And whatever additional strengthening that we need to do, we should do that. And in any case, 100 years, 75 years, 100 years old structures require help. We need to verify that they don't need help and then leave it, or if they require help, provide that.
Okay, excellent. Again, from Muhammad Irfan, is it beneficial for us to understand the measures or techniques used to build heritage structures which help them to withstand and resist past earthquakes events? Of course, you would say
Yeah. See, I must say this, that there are two schools of thought. One school of thought says that heritage structures are safe because they've been lasting for 500 years, 600 years, 1000 years. But the truth is they have not been shaken. But where they are shaken, for example, 2001 Gujarat earthquake, we lost about 30,000 such heritage properties, right? And which is a very large number for one earthquake. And history is a testimony that masonry structures are not standing during strong earthquake shaking, be it in the Himalayas, be it in the peninsular India, anywhere or worldwide. It's not going to be capable of resisting, masonry is not capable of resisting earthquake shaking. 1993 Killari earthquake, forget about historic structures, even regular stone structures that did not last. We lost 8,000 people. Not good for us, not good for us.
Okay. Question from Padmalochan Rawat of Odisha. How the energy released by the earthquake is absorbed by the structure?
So what you do is you put what are called fuses. So in let's say a building, we say damage will occur in beams only and not in columns, not in beam column joints, not in foundations, not in soil. So it's just the beam ends that will form plastic hinges, let us say. So when the building goes back and forth, rocking back and forth, these plastic hinges will do a cyclic hysteretic loop, and the amount of energy that is inside each of these loops is the energy that it is absorbing or eating or drinking from what the earthquake is feeding to the building. So if the building were not to absorb that energy, large amount of energy is fed by the earthquake, the building will continue to oscillate back and forth for another 2-3 hours after the earthquake until structural damping slowly decays it to zero. Right? That is the large amount of energy that will be there during in the near field. In the far field, it will be lesser. So that is why we have to quieten down these structures quickly. If classical design procedure is to have damage in beams, but the new understanding is that we can do base isolation, where we absorb energy in the base itself and send only a limited amount of energy upwards. So that's another strategy to choose the locations where energy will get absorbed and provide devices for that.
Okay.
Yes.
Pankaj Singh says, is there any codal provision that architect cannot deliver design without structural consultant stamping?
Well, I don't want to get into the crossfire of architect versus structural engineer. Okay. I would simply say this, that it is left eye and right eye. I won't choose between the two. And those of you who are interested in answering this question, please read NBC 2016, the administration section. It gives you detailed answer on this question, and there is no doubt about what is written there, right? So please read NBC 2016 on administration.
Very nice, sir. Question from Sangeeta Pandey again. Why the present day structures are aging so fast? They're not even, surviving the service life.
Yeah, if the engineer survives at the site, the structure will survive. If the engineer is not surviving at the site, how can the structure survive, right? So we are paper tigers. We do everything on paper, not at site. We have to go to the site, spend tireless number of hours to make sure that the drawing is converted to reality. That is the site activity. But more importantly, the original design itself, whether the concepts have been converted into design, is the bigger question. And since nobody has been taught this subject in any college in this country, today, as I'm speaking, it's not compulsory in any college in the country. I am embarrassed to say that this is not the model for protecting 132 crores of people, out of which 80% are sitting in seismic zones 3, 4, and 5, which means 100 crores people are sitting in seismic zones 3, 4, and 5.
True.
79%, 78, 79% are sitting in seismic zones 3, 4, and 5, population percentage.
True, sir. Very true. Yeah, question from Megashri M. IS 1893 states that dynamic analysis should be performed for structures greater than 15-meter height. Why?
Well, if you notice that the taller is the structure will oscillate in not just one mode, which is the fundamental mode, but also in higher modes. Because the natural period of the structure will cross half a second. And if you see on the spectrum, the half a second is where the horizontal part finishes, and then the dropping part comes in. So if the first mode goes into dropping part, the second mode comes into the top part. And that means higher modes are going to take more force, and higher modes will start oscillating, which is why the equivalent static method, which is based on the first mode, is insufficient. And so we need to bring higher mode effects, and so we have to do the either matrix analysis, or you have to do the modal analysis if it is linear analysis. If it is non-linear analysis, don't do modal analysis, not valid.
Okay. Question from Chandu Kolanu. During earthquake, it is obvious to the structures to get collapsed, which were not designed under earthquake resistance consideration. However, I don't understand why some portions of the structures retain. Okay, so
well,
yeah.
Let me give you a very difficult comparison. When you die, only your heart fails or your stomach fails or something happens, right? All of it doesn't fail. Whichever part is deficient, that will go. And likewise in structures also, the deficient parts go first. Earthquake is a very fine teacher and fine grader also. It has a red pen in its hand. It will mark all those areas which are actually deficient and quickly take it away with itself. It's not easy. It's not easy. It's very simple that known mistakes, please avoid them, and make sure that the wisdom provided by the past experiences are carried forward.
Very true, sir. Earthquakes are very clever. They always
very clever. The best teacher.
The weakest parts only. I think we have taken a lot of your time. Maybe Professor Chandan Ghosh, would you like to make any comment now? We will give him a little rest. That's what I thought.
I've spoken for 8 hours in a stretch. No rest, because the next earthquake is coming anytime. If I start resting, what will happen?
There are actually plenty of questions. Anyway, okay. Can you throw some light on structural reliability in mitigation of disaster? This is from Rishikesh.
Yeah. See, structural reliability is one word for all the good things that I've spoken in the last 1 hour, right? It's just one word. How reliable is my structure? It will be reliable if you do proper load estimation, if you do a proper structural analysis, if you do proper design, proper detailing, proper construction, right? All of this, if you do properly, then reliability will be high. If any of it is not done properly, reliability is not there. As of now, I will not do structural reliability because I am not doing the basics properly. I don't know how to do modal analysis. I don't know how to do time history analysis. Why should I talk about reliability? I should do all these things properly first. So countries which have done all these properly have a techno-legal regime in place, which means their municipal offices do check the designs of every structure that is submitted for approval. Then I will talk about reliability. But as of now, we are not doing any of this. Basics aren't in place. So why are we going to build that 11th story of the building without building the first 10 stories of the building? So please keep reliability for a sunny day, which is going to come much later. As of now, let's do the hard work of the basics of mitigation.
Okay, thank you. Dr. Amita wants some insight on soft story buildings.
Yes, madam. Soft story buildings. These are very exciting, but very difficult to survive during earthquakes, right? In fact, if you see the 2000 one earthquake, 430 plus buildings fell down. So open ground story buildings fell down. So we don't call them soft story, we call them open ground story buildings, because both the strength and stiffness are deficient. To begin with, stiffness is deficient. And stiffness is almost 1/10 of the stiffness of the upper stories. So if in a multi-story building, one story has 1/10 the stiffness, lateral stiffness, all the deformation will go into that, because earthquake says, whoever is flexible, I'll go with that person. And then so it puts that story into large amount of lateral displacement. So if it is open ground story, that story is going to collapse first. Large deformation will happen. Deformation means relative displacement will happen, and columns will be put to extreme amount of rotational demand, which they cannot carry. And that is why open ground story structures are prohibited to be used with just these slender, darling 9-inch columns. You have to use structural walls in them from the foundation to the roof, not just in the open story or not just halfway down the building. No, take it all the way till the roof. I assure you, you'll reduce the cost of the building, especially you will suck away a lot of steel from the columns and beams. And so please use structural walls from now on. If you want to have the earthquake resisted, moment frames are the wrong systems. For strong earthquake shaking, internationally it is observed that structural walls are essential to reduce the collapse of the moment frame structures. So we need to take off from there and ensure that we add a structural wall in every structure that is going to be subjected to the strong earthquake shaking.
Thank you very much. Nitish Ambale, a student from Mysore, he asks how to plan and implement effective resilient structure, maybe from earthquake point of view.
Is he a student?
Yeah, he's a student.
He's a student. So he, first of all, he has to attend all classes. Second, he has to read all chapters. You cannot leave columns in option questions. You know that 5 out of 8 questions. That system has to be dropped. All 8 out of 8 questions or 5 out of 5 questions. No elective, no optional questions. First thing is he has to learn all subject. Second, he has to graduate not with just the basics, but also basic level of skill, which means he has to do minimum master's program. And skill, when I say it, is tools to do structural analysis. And that tools will be taught to you at the master's level. You will learn that. And then only you will get started in your profession. If you want to study further, of course, nobody will stop you. But master's will require is minimum requirement for you. And then later listen to your seniors. Everybody at the age of 21, 22 want to become CEO and managing director of a company. Please become. But be assured that you may not know much about the world. So as of now, the key thing in earthquake disaster mitigation is to follow the leader. There will be a leader in your organization, follow that leader. In a college, it is your teacher. In your office, is your boss. Follow the leader. If the leader is wrong, leave that organization, go to another organization where the leader is good.
Okay, I think we shall stop at this stage, sir. There are many questions. If possible, we will see whether we can post it to you for answer. Otherwise, I sincerely tell you, it was a fabulous session. Lot of learnings for each one of us. And as was mentioned by Professor Vijayendra, I would like to say that, we will try to see that this is disseminated to as many people as possible. And this was wonderful. Clearly, awareness at all levels, from students to teachers to everybody, construction engineers, a lot of learnings today. Thank you very, very much from my side. And so I will now hand over the session to Professor Kanmani to finalize the things.
Thank you.
Thank you, sir. Thank you, sir. Thanks to all the professors for their very interactive and interesting panel of discussion, rather than a formal QA session. Now I request Professor Rajit sir of Department of Civil Engineering to propose vote of thanks. Rajit sir, over to you, sir.
Thank you, Kanmani madam. Good evening, everyone. As we have come to the end of 6th lecture on online training program on futuristic research in disaster resilience, it's my privilege to propose the vote of thanks. On behalf of Department of Civil Engineering, Vidyavardhaka College of Engineering, Mysuru, and National Institute of Disaster Management, Ministry of Home Affairs, Government of India, New Delhi, I convey my sincere thanks to the speaker, Dr. CVR Murthy sir of IITM Chennai for sharing his knowledge and experience. Thank you, sir.
Thank you so much. Thank you.
Further, I wish to thank all the participants for your active participation in the session. I also wish to convey sincere thanks to the technical team, faculty, and staff of the departments of Civil Engineering, NIDM, and finally, I thank all the participants, all the concerned, and we look forward to seeing you all in the next session. Thank you all.
Thank you. Thank you.
Thank you, Rajit sir.
Thank you.
Dear participant friends, let us break for 1 minute to switch over to our next session on landslide mitigation inputs from rock engineering by Dr. Mahendra Singh, Professor of IIT Roorkee. Stay tuned. We'll be back in the same link in a minute. Thank you all.
Thank you, Murthy. Okay.
Thank you.
Thank you. Thank you, sir. Thank you.
Thank you, sir.
Thank you.
Thank you very much, sir. Thank you.
Grateful. Grateful.
Nice of you.
We have all heard change is the law of nature, but time and again it has been shown that change is also the law that governs technology. With every passing day, technology requires us to create change, evolve, and accept to handle it better. Each passing day, we as engineers hunt new problems and find solutions to them. And we don't stop at it, we better the solution. Change is challenging, yet change is rewarding. And we have changed. We are now autonomous.
Hello, everyone. Good evening. Welcome back. We're very happy to have you all in this 3-day online training program, Futuristic Research and Disaster Resilience, jointly organized by Vidyavardhaka College of Engineering and National Institute of Disaster Management, New Delhi. Now it's day 3, session 3, the last session, but still an effective interaction and interesting session on landslide mitigation, inputs from rock engineering by Dr. Mahendra Singh, Professor of IIT Roorkee, who is here along with our panel members of professors from NIDM and VVC Mysuru. To begin with, let me invite Professor Girish P. Sir, Assistant Professor of Department of Civil Engineering, to welcome the gathering and brief us about Mahendra Singh, Professor of IIT Roorkee. Over to you, sir. Girish, sir.
Thank you, Kanmani Madam. Good evening. Thanks to each and every one of you for being here with us today. I am very pleased to welcome you everyone present on this occasion of the 7th lecturer of online training program on futuristic research in disaster resilience. Being organized by Vidyavardhaka College of Engineering, Mysuru, and National Institute of Disaster Management, Ministry of Home Affairs, Government of India, New Delhi. First of all, I have the pleasure in welcoming the eminent researcher and today's speaker, Dr. Mahendra Singh, for the occasion. Welcome to you, sir.
Thank you very much.
I also welcome Professor Chandan Ghosh of National Institute of Disaster Management, New Delhi. I welcome Dr. S.K. Prasad, HOD, Department of Civil Engineering, VVC Mysore. I welcome Dr. H.S. Dayananda, Dean Academic Affairs. I welcome Dr. Umesh P.K., Professor Kanmani, Professor Raghavendra, Coordinators, Research Studio, Department of Civil Engineering, VVCE. I take this opportunity to welcome guests, all my colleagues and students. Most important for any activity is the participants. I know all of you have come together in large number to listen to Dr. Mahendra Singh. I wholeheartedly welcome you all. I welcome each and everyone. I have a pleasant duty to perform, that is to introduce Dr. Mahendra Singh to all of you. He doesn't need any introduction, and I also have cut short stating many of his achievements. Dr. Mahendra Singh is a professor of Geotechnical Engineering in the Department of Civil Engineering at IIT Roorkee. He earned his BA in Civil Engineering from MNR Engineering College, Allahabad in 1983. MTech in Water Resource Engineering from IIT Kanpur in 1985. PhD in Geotechnical Engineering from IIT Delhi in 1997. His area of interest are landslides analysis and mitigation, stability of soil and rock slopes, rock mechanics, strength and deformation behaviors of jointed rocks and rock masses, tunnels, and underground excavations. Dr. Mahendra Singh has over 30 journal publications, 20 conference publications, 3 books, and 5 book chapters. He has received Best Paper Award for more than 15 papers from various reputed organizations. He has supervised 11 PhD students and several master students. I deem it an honor to present you to the audience for delivering the 7th and final lecturer of online program on futuristic research in disaster resilience. Over to Kanmani Madam. Thank you.
Thank you, Professor Giri, before I hand over the session to the speaker, I have few things to remind you all. Dear participants, if you have any queries to ask our speaker, you can post them in the chat box along with your name and location. Those questions will be taken by our panelists after presentation. And the feedback links will be posted in the chat box. Kindly give your valuable feedback. So dear participants, kindly note that the e-certificate will be issued to those who have registered in NIDM portal and on submission of all session feedbacks. Now, without further ado, let me hand over the session to Dr. Mahendra Singh, Professor of IIT. Over to you, sir.
Thank you very much, Madam Kanmani, and thank you, Professor Girish, for introducing me. And thanks, Professor S.K. Prasad, my old friend, Dr. Ghosh, he has been guiding us for landslide kind of the things, and Dr. Umesha and other dignitaries and dear participants. So let us go to the lecture. I'm trying to share it, so can entire screen I'm trying to share.
Yes, sir.
So the share button is not working. Mhm. Okay, let me try to share the window. Okay, is it visible now?
Yes, sir. It's coming. It's rotating, sir. Yeah, we can see your window, sir.
Yeah, in fact, but there is one video also. I wanted to share the entire screen. So let me start, and we'll try to see if the window is also, that is, video is also available.
Yes, sir.
So am I audible?
Yes, sir. You're clearly audible.
Okay, so welcome again. Welcome everybody. So after such a nice lecture, though I could not hear it in the beginning, I'm now taking you to the other side. Inputs from rock engineering, and especially for landslide mitigation problem. Dr. Chandan Ghosh is there. He's a well-renowned person, and he has been guiding us for these kinds of the things. So I'm going to talk about something, inputs from rock engineering, and I'll be more general because this is a course which probably at most of the places is not taught. So I'll be more general, and let me start. So This is the content of my talk.
Excuse me,
So
sir.
I'll be.
Excuse
Yes.
me, sir. Sir, have you shared your presentation, sir? A slideshow?
No.
We can see only the PPT, sir. We're not
Yeah.
able to see the presentation slideshow, sir. Kindly stop sharing and reshare again, sir, so that we can see the slideshow.
Okay. Let me.
Yes, sir.
Share screen. Okay, share screen. And then entire screen I'm putting. It's
Yeah, now you can hide the button and start your slideshow, sir. Click on hide button and start presentation, sir.
Is it visible now?
Yes, sir. Now we can see, sir.
Okay, sorry for the inconvenience.
No problem, sir. No problem, sir. Thank you, sir. Now you can go ahead, sir. Thank you, sir.
Okay, so a little bit general I'm going to talk about, and I'm seeing I see that many of you people must not be knowing much about rock mechanics. Then I'll initially talk in general, and then I'll go to the very important things which in every geotechnical engineering problem you do. What is the failure mechanism? And then I will go to the uh, discontinuities, means the joints which are present there, how to graphically represent, how to present uh, the discontinuities. And other aspect, then I'm going to talk about the shear strength, because this is a very important issue for rock mechanics. For soil mechanics, you have more confidence, but for rocks, we don't have that much confidence. So I'll be talking about these things in my subsequent lectures. So coming to the general thing, everybody is familiar with this term landslide. It's a very wide term, and when we heard this term, what comes to our mind is that in general you can say this is the downward and outward movement of slope forming materials, and those materials can be a rock, it can be soil, it can be any artificial fill, or it can be any complex combinations. So there will be a very complex kind of the mechanism which will involve falling, toppling, sliding, and so on. So these are the kinds of the things which are going to happen in case of the landslides. And a large area gets affected. So I have shown here one of the landslides in our state. You can see it started from here, and then you can see how much area it is affecting. So this is very important issue, especially for the hilly regions. And I'm focusing on the rocks. Now, in geotechnical engineering, as I said, that failure mechanism is very important. I hope in all branches it is all branches, all disciplines of civil engineering, it's very important. So when we talk about the mechanics, we need inputs from soil mechanics, and then we need input from rock mechanics. Soil mechanics is very well developed, but as far as rock mechanics is concerned, we are still in a development stage. Soil, when you see, you can consider it to be isotropic, you can consider it to be homogeneous, and even you can consider it to be continuum. And in general, in many cases, we assume that there is a circular failure surface when you talk of slope stability analysis, etc. But when it comes to rocks, the rocks are not so simple. Generally, we feel that whenever you get the rock, you don't have to worry about it, but it's not so. Rock is very complex in the sense that it has fractures which we call as planes of weaknesses. So if you look at this photograph, you can see here these are fractures there, and they make the mass very heterogeneous. And also a term which I'm using is discontinuum. It's not a continuum uh, uh, as it is. It becomes a discontinuum, and then failure mechanism is very, very complex here. It is these are the fracture planes, and in fact, if you look at this photograph where I'm showing this line here, so these are the fracture planes which are going to govern the mechanism. So the rock mass can slide along these fracture planes, and they are going to govern the failure mechanism. So this is one aspect which we have to appreciate when we deal with rock. Second aspect, as I told you, I'll be touching some this also, though most of the times I'll be focusing on the first aspect. But second aspect is shear strength. You all from civil engineering background know that shear strength is a very, very important phenomena when you talk of any geotechnical engineering aspect. And again, for soils, you have more confidence, but we don't have that much confidence as far as the jointed rock masses are concerned. I'm using the term jointed rock masses. In the field, you are going to have jointed or fractured masses only. So shear strength is very complex. And if you talk about the landslide problems, the stress level is very low. And when stress level is very low, there is a lot of dilatancy and lot of non-linearity in the strength behavior. So it becomes a complex mechanism, complex thing to determine. And also the rock will be having anisotropic strength behavior. So let us come to the mechanism of slow failure. And before going to that, I'll be using some terms in my lecture. So let us be familiar with those terms. First term which I'll be using is intact rock. When I say intact rock means material between the unfractured. It is the unfractured block which is between the discontinuities. Say, for example, if I take this drill core, then this material, this substance, I'm going to call as intact rock. So this is going to have very high strength, very high very high modulus of deformation. And if I talk about the jointed rock, it will not be having that much high strength or modulus values, though those values will be quite low. So first term is intact rock. Second term which I'll be using is a joint. Joint is nothing but a fracture. We use commonly a term joint, though in joint, when you talk about steel structure is something else, where two members are joined together. But here it is opposite, where the rock is broken, we call it joint. So here you can see in the photograph, right hand side, I have given a photograph here, and you can see a boat here, and in the boat you can see one person also, and you can see the magnitude of these fractures and the blocks. So these are intact blocks, and these are the fractures. So the break of the joints are fractures of natural origin, and in the field there may be very small or movement along these fractures before you construct a foundation, or there is any structure over there, it comes over there. So this is another term which I am going to use. The third term is jointed rock. Jointed rock means any rock which has a joint. Say, for example, this particular core, it is a jointed rock, but it is not mass. So finally, I'm using a term rock mass. Rock mass means there is large number of blocks, intact rock blocks, which are separated by the discontinuities. Discontinuity is another term which we use commonly for all kinds of these discontinuity in the continuity of the material. It can be a bedding plane, it can be a foliation, it can be a joint also. So here in this problem, you can see it is a rock mass. It is rock mass, and here it is jointed rock. So these are the terms which we will be using frequently: joint and jointed mass. Now I come to the failure mechanisms or failure modes. What are the different possibilities? How the failure occurs in case of rock slopes? As I told you, these planar features are going to play very important role. So first failure mechanism, there are different types of the failure mode. The first one is planar. Planar means there is a wedge here. There is this is the joint plane. This is a planar feature, and there is a block here, and it slides down. Similarly, here there was a block which has slided down. So here it is called as planar failure. So for this planar failure, it is necessary that this discontinuity, when it comes to the toe, it should daylight. Daylight means it comes out of the slope here. So then there will be possibility of planar failure. So this is first kind of the failure. Secondly, what can happen is we call it wedge failure. Wedge means now there are two joint planes. You can see here one joint plane is like this, another joint plane is like this, and all of you are coming from mathematical background, and you know that when there are two joint planes, they intersect on a line. So this is the line of intersection. So this entire wedge can slide down. So that is another possibility. And in fact, if the angle between these two joint plane becomes 180 degree, it becomes a planar failure. So planar failure will be a special case of wedge failure. So here I have shown it in this diagram also. So there's the wedge, and it is trying to slide over these planes. So it can be in touch with these planes. It can be in touch with only one plane. There can be detachment from one plane, and so on. So this wedge will try to slide down. Here also in the second figure also has shown some of the wedges which are trying to slide down. So that is the second mode of failure. Third one is when there are blocks. You can see here the fractures are like this, and the fractures, in fact, let me just go back to the previous slide once again. One condition which was here, that this joint plane was going in this direction. I'll be defining these terms again later on. So it was, joint plane was going in the same direction in which the slope is also dipping. Similarly, for second case also, here also the slope was going in this direction, and the line of intersection of these two planes is also in the same direction. So the sliding was possible there. But now here, the major fractures are going in opposite direction. Slope is dipping in this direction, and major fractures are going in this direction. And it usually happens that there are secondary fractures. Because of that, these block formations take place, and then it topples down. So it is the geometry of the block which becomes very important in this case, and we will touch upon these issues later on. So this is called as toppling. So you can find a lot of toppling failures, and the blocks will topple down and come to the toe of the slope. Coming to next one is we call it circular. It is the same as you have studied in soil slopes, so I'm not going to talk much about this. What happens is, if there are very large number of fractures and the spacing is not that large, so ultimately it becomes a slope like soil, because it's a very large slope. So it is a scale also is very important. Block size is small, and there are fractures, and the fractures, none of them is having very quite dominating kind of the behavior. So you can say it is just like soil. So we can use the soil mechanics theories, and generally we use them for this very highly fractured isotropic. Yes, this is the condition which it should sort of satisfy, that we should be able to see that it is isotropic kind of the behavior. One more possibility happens when you have very steeply inclined fractures, and they make the rock, they convert them into slender columns. So this becomes a problem of, you can say, the mechanics, in the sense that flexural buckling failure can occur. So depending on the weight of this column, then it can break here depending on the its modulus of rigidity, etc. So those theories are already known to you. So this is another possibility when there are steeply inclined joint planes. Coming to the mechanism now, so there are two possibilities, as I told you. There is sliding possibility, there is toppling possibility. Flexor I am not touching here much, because it needs that mechanics you have studied in strength of material like subjects. So mechanics of these phenomena is very simple. What you do is it's a simple a thing which we have studied. So there is a block which is kept on the sliding surface. The weight of the block is acting in downward direction. I can resolve it in two components. One is normal to the surface, another one is tangential to the surface. This component, which is normal to the surface, it gives you the reaction, and from there you find out from your mechanics principle what is the maximum resistance it can offer. So what is going to happen if it is a gentle slope? Then this maximum limiting value of resistance will be quite large as compared to the destabilizing force, and this will be stable. Whereas if it is a steep slope, in that case, steep block or steep ground plane, then this shear stress, the shearing tangential forces will be quite large, and it is going to slide. So this is the simple mechanics which we will be using with some modifications. Say, for example, if there is water in the crack, so this is the block which has detached. It is kept on the, it is based on the sliding surface, and there is a tension crack here. So water is going to enter here. Water pressure is going to act on the surface here in this direction, and from here to here the water is going to dissipate. So here the water pressure is going to be maximum. Here I am assuming if it is freely draining, then there will be zero water pressure. If it is not freely draining, if it is blocked, then you may have very high water pressure here. So we can consider the equilibrium of this body, and then we can find out the factor of safety. Basically, factor of safety is how much force is available, which is resisting the sliding, and divided by how much force is trying to destabilize it. So we can resolve all the forces, weight here in this direction and in this direction, water pressure acting on this surface, the water pressure acting on this surface, and we can take their components, and then we can calculate the factor of safety. This is the basic mechanism. If you have a rock bolt like of thing, there is some tension cable, or you have bolted here, it is reinforced. So this force also we can do the mechanical analysis. A T is the force which is being applied by the anchor. I can resolve it in this direction and in this direction. So it is going to increase that normal reaction, and you can add it here in the numerator in the strength, and in the and also this component, the component which is parallel to the surface, it is going to decrease. So these kinds of the analysis we can do. So the mechanics is mathematics is very simple. If I talk about I was saying that for toppling, we have to consider the geometry. Geometry is very important. So if there is a block here, and let us say the block is kept on an inclined surface, and it is having some dimensions, let us say delta x and y. Now everybody knows that if this plane is very steep, and then if I draw this line which is passing through, this is the center of gravity. So if this line is out of this corner, it is going to topple. If this line is within this corner, it is not going to topple. So for toppling to occur, the condition is that the angle, this angle should be steeper. So if I talk in terms of 10, then 10 psi p should be steeper than this value. This is the limiting case when the line is just passing through this corner. So if 10 psi p is more than this, toppling is going to occur. And also, I can check it for sliding also. So sliding is going to occur when this is more than the inclination is more than the friction angle. You all know it. So let us say friction angle is phi or phi j. Then the sliding is going to occur. So when we do the analysis, the possibility will be there that it can be only sliding case, or it can be only toppling case, or it can be sliding and toppling both, or it can be neither sliding or nor toppling. Now this diagram is a very interesting diagram here, where we have shown here on the x-axis the inclination, and here it is the ratio delta x upon y. And this curve, this is the 10 side, so 10 of this angle. So if for a particular case, if this 10 psi p is more than delta x upon y, toppling is going to occur. So the points will be lying on this side, and so this gives us the boundary of the toppling, whether the toppling is going to occur or not. And similarly, if I draw a line here which shows the phi value, let us say phi equal to 35. So this gives the boundary. So I can decide, depending on the block size, whether it is stable block, or there is sliding only, or there is sliding and toppling, or there is toppling only. So we can work out all these combinations from this simple diagram or mechanics. Now here, when I was talking about the angles, when you go to the field, now there are joint planes in the field, and we have to have a sort of presentation of this joint angles there, in which direction it is dipping. So that is one very important thing, direction of dipping, and also what is the angle at which this plane is dipping, the surface is dipping. So angle of plane with horizontal. So we use, so there are another few terms which are coming into picture now. So I'll be using this term, dip and dip direction. Dip means, this is, I have given an example here, this is the roof, and what is the angle of this roof with the horizontal, that is called as dip. So this is the dip. So here in the joint plane I have shown it, dip is here, and dip direction means in which direction it is going. So whether it is going towards north, it is going towards south, it is going towards east or west, that is called as dip direction. So dip direction will be measured in the plan like this, and dip will be measured in a vertical plane like this. So these two things are very, very important, because when I was discussing that sliding can take place if both the directions are same, plane and slope face, both are going in the same direction or not. So these things are very, very important. So we use what is called as stereographic projection for representing the dip and dip directions. So stereographic projection is used for 3D orientation. Data is presented in 2D. So what we do is, like, you have your orthographic projection where you have horizontal plane and vertical plane. Here we have a hemisphere, imaginary hemisphere, and we assume that every plane is passing through the center of this hemisphere, and this is the plane which is passing through this center of the hemisphere, and we are talking about the angles only. So here we are going to plot the angles. We are not talking about the distances. So, and there are many systems. We generally use what is called as equal area angle. So what it does is that uh, here is the hemisphere, and then we take, this is the plane, and I take the intersection of the plane with the hemisphere, and then I will project it at the ground. So if I, let us say there is a point here, and then every point we take about this and we rotate like this. So we rotate it like this. So every point goes on the horizontal plane. So if it is a plane, then when I rotate and bring it over here, so on the horizontal plane, you are going to get this kind of the projection. So it is projected on a horizontal plane. So this circle, it is going to represent the dip and dip direction. So here again I have shown the same thing. This is uh, the intersection, and this circle is projected over the horizontal surface, and this now is going to represent what is called as stereographic projection. So finally, you are going to have this kind of the figure. So say, for example, this is a plane, and this plane is going in this direction. And you can simply imagine that, okay, the plane is having this much angle with the horizontal. It is its dip direction. And this amount here, it is going to be the angle of the plane with the horizontal. So this represents its dip. Let me try to have you much more feeling about this. So what we do is to plot these stereographic projections. We use this equal area net, and I'm trying to now run that one. Let me try to have one small video so that is it visible? Can anybody? And there is a one pin, and put it here at the center. So this is the way we are going to plot these stereographic projections. And now I click the drawing. So it is a sheet. Place it over here. Okay. Madam, can you respond? Is it visible? Outer periphery of the circle. And then mark north, south, east, and west. And now I'm going to plot a plane here. And let us say the plane is having a dip of 40 degree and the direction is 0, 0 from north. So I start with the direction. So from north, measure 80 degree up to here. So this is 80. Mark the point here. Now bring it over the east-west axis. And then from periphery, measure 40 degree. Okay. Is it visible?
Yes, sir. It's visible and audible.
Okay. And then draw this great circle. So this plane is going to, look at this. So there is a plane which is dipping in 80 degree direction, and this amount is the amount. Let us plot one more plane, the plane 2, and dip is 50 degree, and the direction is, let us say, 160 degree. So I put north at 0, then measure 160, 30, 40, 50, 60. So this is plane number 2. Put it on east-west axis, and then from here measure 10, 20, 30, 40, 50. Draw this grid center. So I bring north back to north. So this is plane 2. This was plane 1. And here it is the line of intersection. You can find out what is the direction in which this line of intersection is going. So that is called as trend. So this is the trend, and this angle is the plunge. So this angle is 10, 20, 30, around 38 degree. So this is the angle at which this line is inclined with horizontal, and I can read now. So it is trending in 90, 100, about 106 degree. Okay, is it visible now?
Yes, sir. Yes, sir. It's visible.
Okay, friends. So I have shown how we can use this stereo net, and it gives us the idea that if a plane is on this here, this is north, this is south, this is east, this is west, and if you have a diagram like this, that means it is going in this direction from north, this much angle, and this value on a non-linear scale gives what is the angle this plane is making with the horizontal. So that is what we have discussed. And also I have shown you that if there is another plane here, I can find out this intersection. So the intersection of two planes is a line, and you can find out in which direction this line is going. It is very important. And what is the angle this line is making with the horizontal plane. So Now so this is the thing which I have already discussed. There are great circles, and using these great circles, you can plot the uh, uh, the stereo net, the stereograph, and then you can find out their point of intersection. So this is the plane, and in fact, you can also sometimes we need the normal to the plane also. So the normal will be exactly going in opposite direction. If the plane is going in this direction, the normal will go in this direction. So it will come somewhere here, and this is the angle of the plane with the horizontal, and this will be the angle of the pole. Pole means normal, and this will be equal to 90 minus dip angle of the plane. So it is normal, so difference has to be 90 minus dip. So you can plot the point, the pole is the normal to the plane. Now I come to the application part. So how we decide what kind of the failure is possible? So it is called as kinematic analysis. So here I have shown this is the great circle of a slope phase. So this is the phase. And I have also shown here there is another circle here which I have taken exactly in the same direction, and this is the joint plane. So if I look at this, it is something like this. So this is the joint plane, and this is the slope phase. So the possibility of sliding will be there when both of them are going in the same direction. So slope phase and joint should dip in the same direction ideally, but you can take plus minus 20 if it is going in this direction, one is going in this direction, then also there is possibility. Second condition which it has to satisfy is that slope phase, you see this is the slope phase, it has to be steeper than the joint plane. So joint plane is like this. If you have a joint plane something like this, then possibility of sliding is not there. So there is no possibility here, because it cannot move in this direction. The body can move only in this direction. So slope phase has to be steeper than joint plane. And third and very important condition is that if you know the angle the friction angle of the joint plane, then this angle, the joint plane should be steeper. So if the joint plane is steeper than phi j, then there will be possibility of sliding. Sliding is going to occur. It is acting like a body. So this angle has to be steeper than phi j. So that is the condition for the sliding to occur. So this is the way we decided based on kinematic analysis. And then to do the analysis, then this is the body we take, and it is we can find out its weight. Weight will be acting in downward direction, and the component of the weight you can find out in normal and parallel to the joint plane. Similarly, if there is water pressure also you can find out, you can resolve it, you can find out the water pressure acting here in this direction. From here to here, the water pressure will reduce if it is freely draining. If it is not freely draining, then maybe it may increase like this. So you have to take this area, it is going to act in this direction, and then you can find out the factor of safety by comparing the destabilizing forces and the stabilizing forces. So this is the way we are going to do the analysis. Second is when the wedge is going to form. So here the wedge is going to form. The analysis is same, means so we have to do the mechanics in the same way. But here there are two planes as I have drawn there. So there is one joint plane here, there is another joint plane here. What we do is we find out their line of intersection. So this is the line of intersection, and that line of intersection should be going in the same direction in which the slope is dipping. So this is the dip direction of the slope phase. Line of intersection also should go in the same direction, and that in that case the possibility of the failure will be there. And again here that condition has to be satisfied, that this line of, this is the slope phase, this is the slope phase, and this is the line of intersection which we have calculated. Its angle we can find out from the stereographic projection. I have shown it here. So one plane is like this, another plane is like this. This is the line of intersection. You can find out what is the angle, and then we have to compare it with the friction angle also. So friction angle should be small than the angle of the line of intersection. That is, in that case, the possibility of failure will be there. So for failure, the slope, this is the slope face angle, this is the line of intersection angle, this is phi j, and they should be in decreasing order. Then there is a possibility of failure. We can establish this graphically also. So here this is the slope phase, and we can draw a circle here which shows this, which gives this value equal to the phi angle, the friction angle. And if the point of intersection is within this area, then there will be possibility of the wedge failure. So this is the way we can establish whether there is any possibility of the wedge failure. And when it comes to finding out the factor of safety, so this is the section. So what we do is we will be considering the wedge, we will be finding out its weight, and also we will find out what is the reaction values on the different planes, because it is going to slide on these planes. And then using the mechanics, you can find out the factor of safety. You can find out the reactions, and from the reactions you can find out the frictional force which is going to develop, and then you can find out the factor of safety. I'm not going into the mathematics in detail because here I'm just touching the concepts. So here this is the wedge which is trying to come down, and we can get the factor of safety, and there are some charts are also available for simple cases. So this is the way we can do the analysis. Then if it is there are very complicated cases also. Say for example, there is one joint plane here, another joint plane here, and there may be a tension crack also. So we have to consider this wedge. So the problem becomes very complicated. In fact, you have to use a computer program for that. So basic fundamentals are same, that the weight will be acting in this downward direction. Then there will be some reaction on one plane, reaction on another plane, and then we will be getting those reactions and the frictional forces, and then we will be able to get the factor of safety. So there are standard solutions also available in the literature which can be looked into. I'm not going in detail. So normally we use a combination of the stereographic projection plus these standard solutions. So from the stereographic projections, you get different angles, angle between plane A and plane B, angle of and how much angle the line of intersection is making, etc., etc. And then these formulae expressions are available in the literature, using which you can very easily get the factor of safety even without using the computer programs. Now I'm coming to the last failure mode, that is the toppling failure. So as I told you, the geometry is very, very important here. So these are the blocks. The slope is like this. Slope is dipping in this direction. The joints are dipping in opposite direction. So if you look at this figure, so here this is the slope face which is going in this direction, and these joints have to be steep joint and they will be going in opposite direction, and then there is a possibility of this toppling failure. And this diagram I have already discussed. that this is the basic mechanics which we are going to take into account, that for sliding, the angle should be steeper than phi, and for toppling, this angle should be steeper than tan inverse delta x upon y. So these two conditions, based on these two conditions, we can decide any combination, what is the combination in the field. Normally, when we do the analysis, so this is a example I have taken here. We start with the top block, we check its stability, and then if it is stable, it is not going to slide. Then we go to the next block, let us say, and suppose we find it to be unstable. It may be unstable due to sliding, it may be unstable due to toppling. So we take both of them and then find out how much force it is applying on the next block. Then we go for the next block, and then again we see how much force it is going to apply on the next, and so on. So till we reach the last block. So this is the way we check whether the entire system is stable or not. And finally, this is the last failure mode, which is circular failure. Here, these are the poles of the joint. So there are large number of joint sets. They are so the material is isotropic, and we are assuming that the it is just like a soil, isotropic medium, and we use the soil mechanics theories. And this was the first part where I wanted you people to appreciate that mechanism of failure in slopes, in rocks, is quite different. Now I come to the next part hurriedly, and this is the shear strength aspect. Now another issue is, what is the shear strength? And as I told you that there are two possibilities, that one is when the sliding is occurring. So when the sliding is occurring, the shear strength is required on that joint plane. And second case, if it is a big mass and there are large number of fractures and entire mass is failing, then what we need is rock mass shear strength. So both of them are required, and for that I'll just touch upon few simple models. So first is I'm discussing the discontinuity shear strength. Discontinuity means there is a joint plane, and whether it is a planar failure or whether it is a wedge failure, I want to know what is the shear strength along this joint plane. So far, we have been using very simple model. I simply say take mu equal to 0.65 and use this. Okay, we can do that, but it's not so simple. This shear strength behavior is very complex here. So the first model, which generally is used and very widely used, is the same model which you use for soil mechanics, and the shear strength is given as tau equal to C plus sigma n tan phi. This is the linear Coulomb model. This is the most popular model which we use, but it has been seen that the shear strength is not linear. Here you can see these are the experimental data points, and this is one point, another point, third point, fourth point. Actual behavior is something like this. So we are deviating when we are calculating the shear strength by using this straight line. We are deviating from the actual values, especially if you look at this condition where normal stress is low. So we are overestimating the shear strength. So people have tried to develop non-linear models. So one model is a bilinear model. You can fit this data from the test, and two equations can be used. One equation is for the low normal stress case, where tau is given by this equation. Tau is equal to C sigma n into tan of phi mu plus I. And the second equation is for a higher normal stress. When you are in this range, the second equation can be used. So this is one model. Another model which is very important, and it is very easy to use it. It's not complicated model, and that is called as Barton's model. So here the shear strength is represented as a nonlinear function. So sigma n So tau is equal to sigma n into 10 of, let me call it phi equivalent. So this phi equivalent is this value, phi plus JRC plus into log of 10 JCS upon sigma n. Don't go into the intricacies of this equation. This is a roughness coefficient for which the charts are available, and this is the material strength at the joint wall. It is called as joint wall compressive strength. So the strength of the rock is also going to come in picture. If the strength is low, the strength, if this UCS, this JCS is low, the shear strength will also be low, and if JCS is high, then your strength also is going to be high. So that depends on this ratio as a JCS upon sigma n. So this model can be used for different sigma n values. You are going to get a non-linear kind of the relationship, and that can be used to do the analysis. Here are the JRC roughness profiles which are available in literature. What you have to do is, in the field, you have to have a feel of the roughness, and you can match with any of them. So let us say JRC is 8 to 10, so you can use this value in the analysis. And also you have to include the scale effects. Means this particular roughness is decided, it is calculated based on 10 centimeter of the specimen, and depending on the field problem, then you can change, you have to change that roughness. So you can use this value. Now coming to the next category of the rock mass strength, where I said their entire mass is failing. So when the entire mass is failing, so there are blocks, rock blocks, they are rotating, they are sliding, they are translating. So it's a complex phenomena. And again, for shear strength, then we use the conventional Bohr-Coulomb equation, which is the same in terms of tau and sigma. You can use tau equal to C mass plus 10 phi mass. I am purposely using these terms here. C mass and phi mass will be different from Cj and phi j. Or you can also use the equation in other terms, where it is in terms of sigma 1 and sigma 3. For slopes, this equation will be used. And to get these C mass and phi mass, now a lot of research is going on, but most popular methods are classification approaches. So where you can find out the rock mass rating in the field depending on certain parameters. So like UCS of the rock quality designation, the spacing of the discontinuities, the condition of the joint discontinuities, groundwater condition, and orientation of the discontinuities. So this data you have to get in the field, and based on that, RMR value is calculated, and then you can use this value for finding out C and phi. Similarly, there are other classification systems like Q system you can use. And third approach is, you can also, like we do the test in the laboratory. You see, it is not possible to test rock mass in the laboratory, so we have to simulate those tests numerically. So we use some equations. So a lot of work has been done on that in India also, and abroad also. So we use those equations. So rock mass rating system, as I told you, these are the 5 or 6 parameters which you have to take. So the parameters are the UCS of the rock. Rock quality designation gives you the idea about the fracturing of the rock. So we take only those cores which are 10 centimeter or more than 10 centimeter and sum them up and find out their percentage of represented from the total core run. So that is RQD. And spacing of the discontinuities, where they are widely spaced or their spacing is very low, and whether what is the condition of this the discontinuities, whether they are rough joints or the planar joints, and how much water is present. In fact, in these theories, water is also included into classification approaches. So groundwater condition, whether it is flowing water, if it is water pressure is high or low, Based on that, and also orientation of discontinuities, we find out the RMR, and then based on that RMR value, you can suggest, you can adopt the values of the C and phi. So these values are available from the original contributors, but in India, a lot of work has been done and some modifications have been done for Indian conditions, and we have found that the values by RMR were underestimated. So charts are available. One can refer to those charts. Second classification system which is widely used is called as Q system. So it uses RQD. RQD means again fracturing, how much fracturing is there, then how many joint sets are there, then joint alteration, how much is the, what is the condition, sorry, joint roughness, what is the roughness of the joint, and how much alteration etc has taken place, how much water is present, and if there is some stress, stress reduction factor has been used. So then we calculate the Q, and from Q also then these expressions are available. I'm not going in detail of this. And then you can also use the nonlinear strength criteria for rock masses. So here there are a number of equations available. These equations are from Hook and Brown, where this you can simulate numerically. You can find out what is principal stress at failure for a given sigma 3. So you have to go to the field. From the field, you have to get what is called as geological strength index, and then you can correlate it with the parameters, and then you can have this equation. So uh, in the field, when you look at the mass, then GSI is calculated based on the structure of the rock. Structure maybe sees it is very massive structure, it is blocky structure, and the quality is deteriorating in this direction. And here on this direction, it is the decreasing surface quality. So you can select this GSI value in the field using this chart. So this chart can be used, and one can then do the numerical simulation. Then some theories have been developed in India also. I wanted to highlight these also. So all those who are interested can go into these equations. So these equations can also be used to simulate the shear strength behavior. So Professor Ramamurthy at IIT Delhi has done a lot of work, and you can go into their work and you can find out those expressions using which you can simulate the triaxial strength of the rock mass. We also have done some work at IIT Roorkee, and this work is also available. So one can simulate the triaxial strength. And uh, uh, in these equations, which I talked, you will need the rock mass strength. This is the rock mass strength at sigma 3 is equal to 0. So this is the starting point. So somewhere you would need those values also. So the theories are available. Again, I am pointing out here the work done at IIT Delhi. They have done a lot of work on these theories, and you can then use the equations, or you can also use, there are empirical equations available in terms of classification approaches. Several equations are available which can be used to find out the strength of the rock, and then you can find out the behavior. Uh, Personally, we have also developed some expressions where you can do the test in the field, and you can find out the deformability in the field. You can do the plate load test, and it is easy to conduct. And using that plate load test result, using that deformability characteristic and the intact rock characteristic, you can assess the strength of the jointed rock. We have used these equations at some of the projects where we did plate load tests. We found out the deformability of the mass. Say, for example, here we excavated a small drift, and then we put a jack here and we applied load, and then we found out how much is the deformability. and then from there we were able to estimate the shear strength parameters. So finally, I will just conclude this my talk that landslides are very complex phenomena, and they involve soil and rock slopes. I have concentrated on the rock slopes here. I am not going into much of the mathematics. There are simple failure modes which are possible, and the failure occurs because of the anisotropy induced due to these joint planes. So the failure can be a planar failure, it can be a wedge failure, it can be a toppling failure or circular failure. And accordingly, what I want to emphasize is that you have to select accordingly a particular strength. It is not that I am going to use the same strength in any case. If the failure is taking along a plane, you have to take the strength of the discontinuity. So in that case, we suggest that Barton's model, or you can, if it is possible to test that joint plane in the lab, then you use those values. If it is a big rock slope, and there is a possibility that entire slope is failing, and there is a complex interaction of the blocks are rotating, they are sliding, they are translating, so there is no failure on one single joint plane, then you have to use rock mass strength. So there you can use the classification systems, and then also you can use the strength criteria, and you can find out the strength. What I strongly recommend personally is that some field test should be there. And one such field test I have already discussed. You can conduct the plate load test, and from that plate load test, you can get the deformability of the rock mass as a whole. And that deformability is connected with the deformability of the rock mass and deformability of the intact rock. They are interconnected. If the deformability of the rock mass, if the rock mass is more deformable, it will be having lower strength. So we have found out those correlations. You can connect this deformability with the strength, and then you can find out the strength of the rock mass. So that is all I wanted to say, and I think I have overshooted maybe 10-15 minutes. So thank you very much. Thank you very much.
Thank you.
I'll be happy to interact with you. Sorry for the inconvenience in some of the slides we had.
No. Absolutely no, sir. Thank you very much. Okay. Professor Kanmani, would you like to take up now?
Yes, sir. Yes, sir. Thank you, sir. Thank you, Professor Mahendra Singh, sir. That was indeed an informative session wherein we realized the importance of rock mechanics, understanding the failure patterns, and then stereographic projection of planes, plotting of poles, kinematic analysis, stability analysis, and how to establish possibility of failure and shear strength aspects through different modes. We learned about rock mass strength. Sir?
I have tried to complete the entire syllabus in 1 hour,
Yes, sir. Actually, we learned about rock mass strength and its failure criteria too. Actually, we got introduced to the new topics. And many of us felt that rock mechanics is so interesting and we have to move towards the topic and learn more about it. Thank you for that. Thanks a lot, sir. It was indeed a very good presentation. Thank you, sir.
Thank you.
Thank you, sir. Just a gentle reminder to dear participants, you can post the questions in chat box now also and give your valuable feedback provided in the chat box. Now, in this session, we have our panelist, Dr. Chandan Ghosh, sir, professor from NIDM, Dr. S.K. Prasad, sir, professor and head, Department of Civil Engineering, VVCE, Dr. Umesha PK, professor and coordinator of this program, Dr. H.S. Dayananda, Professor and Dean Academics of Vidyavardhaka College of Engineering, and Dr. G.B. Krishnappa, Professor and Dean R&D from Vidyavardhaka College of Engineering. I request the professors to handle the Q&A session. Thank you, sir. Over to you, professors.
Thank you, Professor Kadmani. As you rightly mentioned, this is one topic, rock mechanics, somehow not touched in the undergraduate level. Therefore, many people will be ignorant on it. So what Professor Mahendra Singh did was, to introduce us through the basics and how, sometimes rock is different from soil, and how sometimes we try to use the same models for rock and soil. And it was really, really very useful. And there have been many good comments on this, as well as, a few questions. So before you take these questions, I just would like to say, Professor Dayanand belongs to civil engineering, and basically a environmental engineer, and he is the Dean Academics. And Professor GB Krishnappa is a mechanical engineer, and he actually is the Dean R&D. So both of them have been very instrumental in our constructive works towards this kind of activities. So they are here too. And before requesting them to talk too, I will first request Professor Chandan Ghosh to give his comments.
Oh,
I know this topic is very, very dear to you also. You have been writing a lot on this.
Okay.
Yeah.
But one thing that to our viewers who are so much rushing towards artificial intelligence, like I talked about IoT, nothing about civil engineering yesterday. But Professor Mahendra Singh has shown that how blended learning can be made through online. He took the stereo net and he has drawn himself
Absolutely.
all those red circles and showing that how slope is. So the kind of it is, again we say that transformation that we have made during COVID period. Again, COVID has changed us, and since most of the students now not able to do their sessional or even practicals, but this his lecture gave a feeling that how practical things can be shown through online, and that too with the stereo net usage of that, and using his own pen and pencil, and we could see his head only because he was using something.
Yeah, he was so engrossed, very,
So
very engrossed.
and not only that, each and every slide, the way that he has taken with color pen and giving a very, very specific authoritative description of the each and every figure, even though they look something like different language for those who have not been exposed to rock mechanics. But that is a wonderful, finally the last lecture of this 3 days program, that where you have, as Professor Murthy also emphasized about the teaching, teaching that is an art which you have
Very
defined in your this lecture.
Thank you.
To all our attendees.
On a lighter side, Professor Ghosh, I'm thankful to my wife. She made that clipping. I was drawing especially.
Great. Okay. Anyway, thank you very much, Professor Mahendra Singh. Actually, before you take up a few questions, I just would like to request the other panelists to share their views. Professor Umesha, please.
Yeah, good evening, sir. I think Professor Mahendra Singh has explained very nicely. It's an excellent lecture. So many failure mechanism, how to solve that one using the structural mechanics and all. He has explained very neatly. I think I will learn a lot from him. I will thank him. I think we will be knowing a lot from this rock mechanics, sir. Thank you, sir.
Professor GB Krishnappa, you can probably mention about your institution innovation cell, and maybe give us some insights about how you would like to take R&D in our institution.
Sir, thank you very much, sir. First, I'd like to talk about this program, what you have arranged. Okay.
Yes,
addressing all the respected people involved in this. Honorable Major General Manoj Kumar Bindar, the Executive Director, National Institute of Disaster Management, New Delhi. Honorable members of our Vidyavardhaka Sangha, Mysuru. Respected Mahendra Singh, Professor IIT Roorkee. Respected Dr. Chandan Ghosh, Professor NIDM, New Delhi. Respected Principal Dr. B. Sadashivegowda. Respected SK Prasad sir, Professor and Head of Civil Engineering, VVC Mysuru. respected Dr. H.S. Dayanand, Dean Academics, VVC Mysuru, and respected Dr. Umesh P.K., Professor of Civil Engineering and Vice President of Institution Innovation Council, VVC, coordinators Professor Kanmani S.S. and Professor Raghavendra, and all respected dignitaries and participants. This 3-day program on futuristic research in disaster resilience, organized by VVC in association with NIDM, is a first of its kind program organized in our institute in the field. It is actually an high impact training program. I have been seeing that the comments on the lecturers, resource persons, each and everyone is gem of, okay? All the resource persons are capstones. In the terminology of civil, we say all of them are capstones in their field of expertise. Congratulations to the organizers for organizing such a wonderful program. I thank them immensely. I thank you all. So actually, I am the Dean Research and Development in VVC Vidyavardhaka College of Engineering since 2016. And we have Institution Innovation Council, which was constituted in the year 2019 under Ministry of Education. I am representing President of that IIC VVC, and our friend Umesh sir is Vice President of that. So under this, actually, we give priority to the research activities. So innovation from students to PhD level. So there are about 77 research scholars in our 9 research centers at VVC. And we have an incubation center. There are 7 startups. They are doing very well. To say that one startup has got 12 lakh rupees from University of Agriculture, Dharwad. And one startup called Dujira Private Limited participated in Lucknow exhibition exclusively for DRDO. So they're actually into humanoid type of research. They invited by the Ministry of Defense to showcase their research in there. Actually, we feel proud of themselves. And another is company called Neuroflares. They are doing. They are actually have clients in Italy. All these are actually our students and alumni only, and they are getting the facilities free of cost. So actually, I feel proud of our management for giving these facilities to our alumni. And also, all the supports are given by our principals to do such type of activities in our campus. And also, we have IPR cell, Intellectual Property Rights Cell, that is VVC Intellectual Property Rights Cell. Through that, we file patents. As of now, about 33 patents have been filed. About 19 have been published. Very recently, actually, we opened that IPR cell. This is it. And through our Institution Innovation Council, we organize lecture series, and actually we invite innovators and startups to present their saga in front of our students as well as faculty. This is a continuous scheme what we have been doing. In addition to that, every semester we conduct mini project competition as well as idea generation competition. That's what we call pitch competition. So during this pandemic, actually, we did not have this mini project competition, but we had conducted idea presentation competition. Good response from the students. And for very bright ideas, actually, we give cash prize. In addition to that, we take them to the mentors for converting that idea into startup. Those startups will be incubated in our incubation center. I thank Professor Prasad sir for giving this opportunity to tell a few points about our research center. Thank you.
Sir, thank you very much. We know how much you are doing, and if at all we have been in research, Vidyavardhaka College of Engineering is in research, your contribution is immense. Please continue those good work, sir. May I
Thank
now
you.
request
Thank you.
Professor Dayanand to share his views, sir.
Good evening, everybody. This 3-day online training program on futuristic research in disaster resilience is related to the theme Ecosystem Restoration of World Environment Day 2021. The present innovative methods did not exist in India 27 years back when we experienced the Lathor earthquake on 30th September 1993. We have not achieved much as on today. The damage was 1.3 billion. Due to climate change, we are experiencing the various types of calamities and disasters, and we are bound to rely on the futuristic research methods to combat and mitigate the disaster and to prevent the damages. In 2018, landslides occurred in Kodagu, Karnataka due to heavy rainfall in August 2018. These events resulted in many damages to existing infrastructure in Dakshina Kannada and Kodagu districts. Over 900 landslides were identified in various taluks of Kodagu, Dakshina Kannada, and other districts of Karnataka using synoptic satellite data coverages. And these were made available to Geological Survey of India, Karnataka State Disaster Monitoring Center, and others, but there was no yield. In his keynote address, T.G. Sitaram, the director of IIT Guwahati, emphasized on sustainable development. He said, small is beautiful. Yesterday, even Professor Chandan Ghosh illustrated many examples on how futuristic research helped in controlling the pandemic COVID-19. Necessity is the mother of invention, is thus proved. This training program was well planned and it went on well for 3 days. It mobilized overwhelming response from throughout the country, fetching one more feather to the hat of Department of Civil Engineering, BVC, Mysore. The collaboration with National Institute of Disaster Management, New Delhi, has brought laurels to the institution, and we seek their support in the years to come. It has certainly opened the minds of young teaching fraternity to take up futuristic research to prevent, mitigate, and to prepare to reduce the damage caused due to calamities and disasters. Futuristic research certainly calls for multidisciplinary approach to solve the problems of civil engineering domain. I thank the organizers and Professor Dr. S.K. Prasad for providing me an opportunity to take part in this 3-day program as a faculty of department. Thank you.
Thank you very much, Professor Dayanand. And you rightly said, a lot of things are there to work with. And as you rightly pointed out, even our Western Ghat slopes are very, very unstable. And probably Professor Mahendra Singh can throw some light on that. And, in future, we may be able to have more people working in this direction. Let me just request Professor Mahendra Singh to answer a few questions because there have been many. Shortage of time, therefore I wouldn't be asking too many. There have been many appreciations. Many said technically very knowledge building, and then many said very nice presentation and so on. Let me go to a few questions. This is from Avik Kumar Mandal. How to get the friction angle of rock mass joints, both in field and laboratory, which is an important input parameter for analyzing different modes of stability of rock mass slopes, maybe modes of failure of stability of rock mass slopes. Can you please throw some light on it?
He has used the term rock mass joint, I think what he means is rock mass. There are two different terms. One is rock mass as a whole. For example, you have a soil mass as a whole, and the friction, when you talk about the friction angle of a soil, it is a friction angle of the soil mass, not the friction angle between two soil grains. So when it comes to rock mass, in the field, it's very difficult. You see, either you do some back analysis, but otherwise, most popular approaches are the classification approaches. You use those classification systems, and then you can get these values. Another is I have already discussed that failure criteria. So you have so many. There are a number of failure criteria. And personally, I feel that for a particular problem, I use many of them, and they give some range. So once that range is available, and from that range, means you have to simulate the traction test values like we do in soil mechanics. We conduct the traction test in the lab. So here rock mass cannot be tested in the lab. So we use those expressions, the inputs from the field, say for example GSI, you can use Q, you can use RMR, you can use RQD, and there are more than 25 correlations available, and you can then have a range, a width of a range of the parameters, and then you can use your own judgment. Obviously, that is the last means for any geotechnical
Yes.
problem, but it gives you the confidence. Okay, my values from using this hook brown to this is like this. They are coming in this range. I'm confident about that particular mass, and then I use those values. So that is about the rock mass. Coming to the joints, there are as I told, Barton's model is very handy, very handy if you use it with scale effects. So, and I have done some experiments in the field that I gave the joints to my students who are not experienced at all. So it's sometimes what people say is that they are biased. So one will be, you have to feel the surface, you have to feel the surface and of the joint, and then you have to estimate JRC. And then from that JRC, you can calculate the phi value. So surprisingly, even without much experience, the student gave the values which were very in a very close range. So I found these techniques very useful. So Barton's model can be used, though there are some other theoretical models also, energy-based models also that can also be used. But Barton model can be used very conveniently. That is my personal feeling.
Thank you. Thank you, Professor Mahendra Singh. You clearly mentioned earlier also that, rocks are more complex than soils. And hence, it's not very easy to predict, where you need lots of judgments. Thank you very much. Another question from uh, Dr. Gomati Nayagam. What is the general characteristic features of North Indian Himalayan region compared to southwestern Ghat region as per Indian experience? Primary cause being rainfall. So he wants you to compare the North Indian Himalayan ranges with Western Ghats. And
Frankly,
probably he says rainfall is the major cause here or there also. He would like you to consider rainfall as one of the causes for the failure. How
rainfall
do you
is one of
differentiate?
the major rainfall is one of the major causes of failure. Here also in monsoon we get so not many slope failure cases. That is the rain is said to be the biggest enemy of slope. That is the common term we use in geotechnical engineering. So it is true that rainfall is one of the biggest thing. Then obviously the characteristics of the particular area, whether you are considering a soil slope or the rock slope, now it depends on particular area. So their Himalayan rocks are very fragile, very means there is lot of variability we have, and lot of geological surprises we get in Himalayan region. So that is the next issue, which is very complicated in Himalayan geology. But
Okay, thank you. Maybe I just would request you to take one more question because afterwards we are already late. So Mr. Rajit asks, how can you stabilize rock slope?
Yeah, there are many ways. It depends on the problem. If you know the rock mass is there, and the very typical thing with the rock mass is at the toe. If you destabilize some of the blocks, the entire the pile of the blocks is going to come down. So maybe a small toe support at a particular place is going to make it much more stable. So, and there are ways, like for example, you can do the reinforcement. You can apply the rock bolts. You can apply the toe support. You can apply any other kind of the support at the toe. And there are other measures which we already know. There's the water ingression is there. You have to reduce that water ingression, and these kinds of the activities can be taken up.
Thank you. Thank you very much, Professor Mahendra Singh, for your excellent knowledge sharing. I think, I thank each one of you right now and hand over the session to the MC because I have a final thing to do. So, yeah, Professor Kanmani, please.
Thank you, sir. Thank you, sir. Added to SKP sir's words, I would like to read one more appreciation from Pankaj Singh, which I thought I should tell this. He has told that it is nicely explained in easy, understandable language of one of the toughest subject, rock mechanics. It was nicely explained in an easy manner, sir. Thank you, sir. Thanks a lot, sir. Thank you for that. And I thank all the professors for that interactive Q&A sessions and your opinion about the 3-day workshop. And I request Dr. Mahendra Singh sir to say a few words on this workshop.
So at the outset, I thank all of you, especially Professor Prasad, for giving me this opportunity to reach the participants. And as I have learned that it has been a wonderful event in terms of learning. I was able to listen to some of the discussions of previous lecture, and it was wonderful. So I personally feel that these kinds of the events will be very, very useful, especially when you have people like Professor Chandan Ghosh also. He's an expert, and means we learn from him a lot. And Dr. Prasad is already a wonderful person. We have been classmates at IIT Kanpur, so that is a personal thing. But the kind of the expertise and the kind of the quality which you people have given is really wonderful. So means I should thank from on behalf of the participants also for you.
Thank
So
you.
that's my opinion. So it's wonderful.
Thank you.
And for me personally, it's very nice because the rock mechanics is a very confined subject, and we have a very limited kind of the stakeholders, not the stakeholders, but the community is very small. So when I interact with other people, it gives me a lot of encouragement, especially from people, as I told you, Professor Bhogosh, Professor Prasad, these people. So it's wonderful for me. Thank you very much. I'm really thankful to you.
Thank you, sir. Thanks a lot, sir.
Thank you.
Thanks for coming
you
to
very
us,
much.
sir. Thanks for explaining rock mechanics in a very simple manner, sir. Thank you.
Thank you.
Professor Kanmani, you can give a chance to Professor Chandan Ghosh also to make a comment on
Sure,
the
sir.
event.
Sure. How can I forget him, sir? He's behind everything. Thank you, sir.
But I
Thanks a
want
lot.
to just, I am mesmerized by all the lectures being given. Each one has got such a distinguished remarks and dimension that it has opened up to the very theme of this 3 days program. And at the same time, just now I got really touched by the kind of innovation cells that you are having. Dr. Krishnappa has mentioned about 8 innovation cell. I would like to add one more, that is on vetiver grass. And my last visit to Mysore, where Dr. Prasad was there, then I have gone to Kodagu to see the landslides. And then next visit I made just 1.5 years back. In 2019 December, I carried vetiver grass and then called community of more than 100. And then we selected one of the site. I want to show that, just only that much. And I want to create that. I want to show that how it has worked. Just I'm sharing a slide, not slide, rather
Please.
Facebook photo. These are all there in my
Go
Facebook.
ahead.
Just only I want to show this slide.
Yeah, sure.
Yeah, you have done a lot on this vetiver grass, and I hope people in and around Mysore will be able to use it for stabilizing slopes.
Yeah, so we would like to add one more innovation center using this vetiver. You see, this is that description is given here. It is a slide number 1600. CG is Chandan Roche. Facebook 1600 slide number. It was flagged on 10th March. You can see application of vetiver grass on a steep slope, which is more than 75 degree. Where I also came down here. I also came down here and packed some of the wooden branch, small branch, just as a nail. Think that 1 feet, 2 feet, they have gone inside. And then it was being shown. You see so many people. This house was about to fall down. And on this, and these are the flexible, flexible rope made into this ladder so that one can come down, because the slope is much more than 45-46 degree that we deal with, or 50 degree we deal with in soil mechanics or rock mechanics. So this slope, and you see that it has come down. So it was a devastating effect in the last few years. And same area, after 6 months, December we have visited along with the vetiver grass. We planted there. More than 100 people were there, and all came on their own. And this is the condition of that.
Great, sir. Great.
And nothing has happened to this house or things. It came up this way. So we would like to take majority of the slide can be handled. Majority, I would say 80% of the such kind of erosion and landslide things can be handled by this vetiver grass, along with some other structural intervention, say breast wall or small laying and drainage. So maybe I would say that let us have an MOU with NIDM.
Yeah. We will surely be able to associate
with NIDM, following up as a follow-up action with you. You make another innovation. Of course, IoT part that I have talked about, all those, there are more than 10 such areas which I want to take it to Mysore when you are taking this, and so that, in NIDM, we'll be very happy to join hands with experts, all the experts here who have been here with us, and also making your innovation center a hub of such kind of activity where local people, we can transfer this. We should not say it is technology. It is a know-how that every people should know, and it is very easy. So
we are happy to collaborate, sir.
So
Thank you very much, sir.
Such kind of things are, is possible over here. So I would like to say that let us say that on behalf of NIDM, our entire group of our teachers, we are 4 professors and 4 assistant professors, and many young professionals are there. And you can see our website. COVID has forced us to do a lot of such online training program. Otherwise, we used to visit physically. Like even this time, I programmed that entire year. I'll take 5 days of physical training program with all the IITs. Like IIT Roorkee also is there, IIT Bombay, IIT Method. That was the program. But due to COVID, till this month, we are not able to go there. Otherwise, we go physically and then make 5 days of program with a lot of practice and site visit. That has been our norms, and entire expenditure is borne by NIDM training grant, which comes out about 5 to 6 lakhs, which we pay entire our visit, stay, everything is paid by NIDM. So we'll be very happy when COVID pandemic will be over, when this MOU will be established, and then we can have a regular visit and do some of your project work, innovation work with such kind of side application. The inspiration is Professor Mahendra Singh.
Okay.
Nice. We'll do that. Thank you so much. Thank you.
Thank you.
Thank you, sir. Thank you, sir. It's so kind of you, and I should say thanks to Corona and the COVID pandemic, because of which great eminent personalities like this are with us together today. And in all the disaster, we are very happy that we all have met together, and we are with so many participants across India. Thank you, sir. Thank you,
every
Chandan sir.
challenge teaches us. Every challenge in the life teaches us. So the COVID is also teaching us.
Yeah. Definitely, it has taught us a lot.
Yes, sir. Yes, sir. Now, I request our beloved HOD, Dr. S.K. Prasad, sir, Professor and Head of Department of Civil Engineering, to summarize the 3-day online training program on futuristic research in disaster resilience, jointly organized by VVC and NIDM. Over to you, sir.
Thank you. Maybe I just would like to share the screen, and maybe I want to use the PPT.
Sure, sir.
Okay. Just tell me whether it's okay.
Yeah.
Okay, sir.
Okay. I'll say hide and then okay. Yeah. I don't know. I'll try to finish in about 7 to 8 minutes. Okay. I just would like to say that, we had this 3-day online training program on futuristic research in disaster resilience from 11th to 13th. Basically, we planned it because, from 14th, we are feeling that there is a possibility of lockdown being removed. And we wanted to do it in the evening so that, people will be tired of work. And then, they will have a lot of energy in the evening to listen to these things, because we found this to be a very appropriate time. And I believe, looking at the kind of participation, this was the right thing we took. And we had the inauguration on the first day, 11th at 4:15. And in the inauguration, we had our principal, Professor Sadashivegowda, and then, we had the personnel from our college management, engineer P. Vishwanath, and then Sri Gundapagoda, who is the president of Vidyavardhaka Sangha. And we also had Professor Chandan Ghosh, who has been there from 4:15 day before yesterday till now and continuously. Then Professor T.G. Sitaram, the director IIT Guwahati, provided the keynote lecture. We had about 45 minutes program, and this was followed by a lecture by Professor T.G. Sitaram. In the first session, he talked about coastal reservoir solutions for disaster resilience. It was an eye-opener kind of lecture, because many people had no idea about how in a large scale we can think about saving our problem with water, and then solution to major water problems. So he says that coastal reservoirs can be a major solution in future, and then dams, whatever we have, they're only catering to about 10% requirements, and they may not last long. And interestingly, he mentions that concrete or masonry dams are weaker than earthen dams, and the order of the day in future would be the coastal reservoir solution. Then we had an excellent lecture again by Dr. Selvi Rajan S, advisor, Nexus IITM Research Park. She spoke about research priorities in the field of wind engineering to restore resilient future. So she gave a wonderful lecture covering all kinds of problems related with wind, whether it is tornado, hurricane, typhoon, cyclone, several things. And then finally she tried to give a message that wind related forces can be very dangerous, especially to tall structures, which has to be taken care of. And she also mentioned that we can learn a lot from nature, especially many birds, and hence like kingfisher, condor birds, to understand how our structure should be to resist wind. Then we had, two sessions yesterday. The first session was by Dr. P. Vedagiri, Professor IIT Bombay. He spoke about proactive traffic safety evaluation using surrogate safety measures. Some people ask, how can this be disaster? But looking at the kind of casualties we have, almost on an average, 1.5 lakh people in India are killed because of traffic problems, traffic accidents. And he very very clearly mentioned that safety, speed, comfort, convenience, economy, environmental compatibility are all the factors to be considered when you look at the transport infrastructure. And in that, safety should get the highest priority. He identified many risks like speeding, lack of restraint system, lack of helmet use, drunken driving, use of mobile phone while driving, and roadside objects are some of the risk factors which create problems. And finally, he gave a wonderful message mentioning that a 2 second rule, 2 second difference between the vehicles, if you can manage as a road safety auditor, you will be helping a lot of accidents to be saved. And then many blind spots will be there, especially if you have heavy vehicles, and the pedestrians or other road users should know where exactly blind spots are there. And he clearly tried to mention that speed can be very dangerous. You have to balance between speed and severity. In case you go in for speed, there is every possibility of serious problems. After that, our own Chandan Ghosh, who has been always there over the entire period of these 3 days, he gave a lecture on IoT devices for disaster management, and he covered various aspects of disaster management, disaster resilience, and not only covering natural disasters. He also talked a lot about COVID. And then he said that disasters cannot be controlled only by the government. Every one of us have to chip in. Very nicely he commented on all these aspects of high resilience. And then he mentioned that we can use simple mobile phones for many of the managements of disasters. And he gave a message that disaster management, disaster resilience requires everyone to show belongingness and work together. IoT can be a very useful tool, to solve problems of disaster management. Shift from analog to digital, mobile phones, AML, health monitoring, wireless devices are all the futures of disaster resilience. Today, we had three wonderful lectures. The first one by Professor Babu Narayan of NITK Surathkal. His title itself was impressive: Nature, Structure, and Future. He gave a very good analogy between, how nature is taking human body, how complex it is, but how systematic it is, how organized it is. If we can understand this well, we can probably understand structural analysis. And then he gave a comparison between birds and airplanes, and then the Shinkansen train, the bullet train in Japan, how it got its shape, via learning from kingfisher bird and so on. So his major remarks were, there are a lot of things we need to learn from nature for future research. Try to imitate nature. And he gave many examples. He said, objects of every day use can teach us a lot. So it could be, paper clip, it could be fountain pen, pencil. So he said, nature is stingy as well as lazy. So he says, it teaches us a lot about optimization. Then we had another wonderful session from Professor CVR Murthy. We know he always he is an excellent teacher, and he spoke about R&D in earthquake disaster mitigation. He covered entire, disaster management, specifically related with earthquakes, exclusively how it should be taken. And then his emphasis was on, creating awareness at all levels. And he finally mentioned that earthquake resistant design is a multi-hazard design, closed loop design methods. Earthquake is not a force; it should be considered, from the displacement point of view. New design methods should be emphasized. At present, we have force-based design, displacement-based, and maybe in future energy-based design. He mentioned that we need to use correct level of technology, and repair is not retrofitting. He actually tried to say that awareness is very, very important, and this is what is to be created at all levels. Finally, we had the lecture from Professor Mahendra Singh. As he rightly said, we have been very affectionate friends, since the days we were at IIT Kanpur doing our masters together. And he spoke about landslide mitigation very clearly. This is a subject which somehow is not clearly taught in the undergraduate level, but we know how important it is, whether it is Himalayas or the Western Ghats, and the kind of knowledge he gave on how to understand the mechanism of failure, modes of failure, were simply fantastic. So I really congratulate and thank him for giving us uh, more interest in this area. And he very clearly mentioned that rocks can be more dangerous than soils, and we have to take extra care about that. Well, I'm extremely happy to mention that all these were, I would say, history. We will cherish these 3 days to a large extent at our institution. And basically, for these to happen, the resource persons, did marvelous job. Equally, we had excellent participation. We had, totally 723 registration at an NIDM portal, and we had a parallel registration in our institution through Google Form 737. And this is what is the list of viewers, and the feedbacks we have already received. Professor TG Sitaram, 2,500 views, 587 feedbacks. Professor Dr. Selvi Rajan, 1,750 views, 415 feedbacks. Then, Professor Vedagiri and Professor Chandan Ghosh, 1,563 views, about 500 plus feedbacks. And in the morning, we had Professor Babu Narayan, 837 views, and it's going to increase further. So during that time, current period, 837, 250 feedbacks. For Professor CVR Murthy, we already had 971 viewers, and then more than 200 feedbacks, and we still have to collect these details clearly. And I do not know if Professor Raghavendra is there. You can mention to me what is the viewership for Professor Mahendra Singh's lecture. Raghavendra is there? Okay. Anyway, I just would like to say thanks to everyone who has made this a possibility. Yeah.
1,686.
Oh, great. Great.
Yes, sir.
Thank you. Thank you very much. Okay. Very nice. So first of all, I'll have to thank all the resource persons. I would say, you made the difference. And these days we have been having so many webinars, and because of that, we have lack of participation, because people do not know which one to attend to. But the kind of support we have got from the participants is mainly because of you people. So starting from Professor TG Sitaram to Professor Dr. Selvi Rajan to Dr. Vedagiri to Dr. Chandan Ghosh to Dr. Babu Narayan to Dr. CVR Murthy to Dr. Mahendra Singh, my big thanks to all of you. Of course, I'll have to thank NIDM. It has taken us to the next level. And over a very short period of time, in about a week's time, all these things happened. So I'll have to thank Major General Manoj Kumar Bindal, Executive Director, for providing all the opportunities. And I do not know how to thank my good friend Chandan Ghosh. It is he who was instrumental for everything. His team, Mr. Kumar Abhinay, Mr. Balaji, and all the technical and administrative team members, my sincere thanks to all of you. And not only for making this a possibility, you also provided us the financial help. Thank you very much. Of course, I'll have to thank my VVS management, Sri Gundappa Gowda, Honorary President, Sri Shivalingappa, Honorary Vice President, Sri Vishwanath, Honorary Secretary, Sri Shaila Ramana, our Honorary Treasurer, and all other members of the VVS management, Vidyavardhaka Sangha management. I'll have to thank my institution, Vidyavardhaka College of Engineering. Proudly, we have Professor Sadashiva Gowda, Principal, and here all of you are seeing Professor Dayanand, Professor G.B. Krishnappa, all the deans, heads of the department, deputy deans, faculty, and staff of VVCE for providing this opportunity. And of course, my team at in the Department of Civil Engineering. I invite all of you to please visit us, and I invite all of you on the stage here also to be part of us. And it is I'm really proud of my team, and my sincere thanks to everyone in the Department of Civil Engineering, including my students. And this team was instrumental in making this program a grand success from Vidyavardhaka College of Engineering side. I do not know how to thank, whether it is Dr. Umesha PK, Professor Kanmani, Professor Raghavendra Sanganaikar, Professor Ajit, Professor Manoj, Engineer Pushkin, Engineer Avinash. My big thanks to all of you. You made this a grand success.
Thank you.
Well, participants, we had people from across India. We also had participants from Africa, Middle East, USA, and more than 800 people were participating in each session, which is incredible. And it was a very active session afterwards also. Panel discussions went very well with many relevant questions and well answered by the speakers. And I do not know how to thank my good friend Chandan Gaur. My big namaskaras to you. And so I finally end. Thank you very much. Good luck to every one of you. I hope to meet all of you in some way or the other, or maybe I'll have another chance to conduct a training program, something like this, perhaps offline. And I welcome every one of you to Mysore and to my institution. And thank you, one and all. Thank you very much.
Thank you, sir.
Sir.
Thank you.
Sorry,
sir.
I was. It was little lengthy. Kindly excuse me.
Yes.
Let me stop.
It's okay, sir. No problem.
Yeah.
Yes, Umesh sir wants to talk, sir.
Yeah.
Oh,
1 minute.
Yes,
So
please,
I would like to thank our HOD, Dr. S.K. Prasad. Because of him, it is work was here. He has helped a lot from beginning to end, starting from the first meeting. Whenever he called, he used to come, and even night used to work up to 10, 12 o'clock and all. I think because of him, it is possible to make this event very successful. I would to thank again, sir. So thank you very much. I think I would like to. I think he already thanked everyone. He's only left out our HOD. Okay, thank you very much, sir.
Thank you.
Yeah,
Thank you very much.
From my side also, that of course we are friends, but we are friends with a purpose to make a relation that we have established, but we have spread our network across the globe through such kind of organization that you have really given a lot of learning thing for us also back at NIDM, especially the summary that you have made, taking care of from the day 1 to the last day, 2 days, updating it. And that is a meticulous work that you have presented in this. I think it is unparalleled even in our case also. So it is a really something I would say that all from our core of heart, from an IDM side, and also from all participants, that everything that you have organized, even it is all A++, if it is there. And so that way, I think it is not that only we had friendship or IIT Kanpur connections or other thing, but it is the team that you have made, whom you have presented, even being at the background. The team making is more important than anything else, and which has been displayed over here, and which is on record. Everything is on record. I think let us expect that we make our country really more resilient, and for future, whatever it is that we are going to do, let us be united. So from NIDM again, thank you, you and your team, and BBC College of Engineering and entire group of staff.
Thank you,
And
sir.
also
Thank you
to all the resource persons.
Resource
Umesh,
persons, excellent. Yeah.
excellent, and the selection and the way that you have arranged each and everything, it has taken us to a completely a new and very momentum. It has given a momentum to the entire the viewership that you can see, which is getting multiple every moment, every second, and you are showing that every hour it is how it is getting viewership is changing. So how many viewership are there? It's by itself in online. It is a count that it has reached to the every people over here.
Correct.
So
Exactly.
finally, what I would like to say that no thanks are enough, but we are always ready to make India really worthy
Good,
and
good.
Thank you.
resilient nation.
Thank you,
You.
sir. Thank you, sir. Thank you so much, sir.
Okay.
You said it's teamwork. We are very happy for that. But this team also includes NIDM members, sir. The members from NIDM, Balaji sir and Kumar
Balaji.
Abhinay sir, along with
Yeah.
great leadership of Dr. Chandan Ghosh sir. We really thank from the Department of Civil Engineering, sir. Thank you, sir. Thanks a lot for that. And we should not forget that this program has become a grand success. It's mainly because of our participants. Their overwhelming response and cooperation has made this program a real grand success. Had made this program. For more such programs, I request the participants to subscribe to our BBC official channel. And lastly, I wish you all to stay healthy, stay home, and stay safe. And with this wish, I, Kanmani SS, signing off as Master of Ceremony for this event. Thank you all. Thank you. Thank you all, sir.
Okay.
Thank you.
Thank you.
Thank you.
Bye.
Thank you, every one of you.
Thank you.
Thank you.
Dr.
Thank you.
Thank you.
Thank you.